Okay, we are now live on the YouTube. Okay, we should be now live on the YouTube.
It looks pretty good.
Okay.
You can see your taskbar though.
Yeah, I know. I just gotta full screen that.
Right. Okay, we'll just get started here then in 2 minutes. More people.
Morgan, the YouTube link is also on the link tree. On the Instagram.
What the heck's a link tree?
It's just a one link that has all the other links in it.
Oh, I'll just follow the link in the chat, but
Okay. Carmen, could you update the slides quickly? I updated a couple of things.
Yep. Is anyone else still editing slides? I'm going to take that as a no.
This might be a dumb question, but are cameras being discouraged here, or like is there a reason why nobody has their camera on?
Cameras are encouraged, but my camera just doesn't work on my computer. So.
Oh, okay. Yeah. Well, in that case, hello, Devin.
That's it.
I wasn't sure. I joined and I was like, why does nobody have their camera on? Like, did something happen?
I believe they're actually encouraged in the notes slide.
Okay.
Okay, let's get started. Welcome everyone to the 10,000 foot rocket critical design review. We'll just be kind of going through all the designs and critiquing them as they come. So if you want to go to the next slide. So the agenda today, so we're gonna do our introduction, kind of just what the expectations of CDR are, more like kind of what you guys or how you guys will be presenting, and then kind of a brief overview, just verbal overview of kind of the rocket. Cool. Next slide. And then Aerostructure recovery and all that stuff. So the expectations video on, you can. I'm being a hypocrite. Microphone muted unless you're speaking. And any feedback or questions, just make a note of them and then and present them kind of at the end of the subsystem presentation or kind of the big project presentation. And we're going to do kind of a 10-minute intermission after propulsion if you guys want to get a bite to eat. In terms of design freeze, so design freeze is going to be when the date is when the team isn't allowed to make any more changes to the CAD and the mechanical design stuff. I know kind of Avionics might need a little bit more time with the software, but mechanically, the design freeze will be happening. Supposed to happen on June 19th at midnight, and yeah, this is to prevent, like, when we're manufacturing. This is just to prevent stuff from kind of changing on the fly while we're trying to make stuff. So try to stick to it, and if any changes do need to be made after that, definitely bring it up to the team. Have a discussion about it. Cool. For the actual presentation itself, I'll have the CAD up, but it would be good if you guys also had the CAD up just to go through it if needed. It might just make it a little bit easier on you guys to kind of convey what you're talking about if you guys are navigating the CAD. But open up CAD as you see fit. If you don't feel like you need to open up CAD to explain something, then that's totally okay too. But otherwise, we'll just take the presentations. So a little overview of the rocket. I mean, all you guys know, I don't think I need to really say much on this. I don't know how many people are in the live stream, but essentially kind of the rocket is going to be our test platform for the air brakes and the MaGP-I project primarily, and then we're going to be also collecting sensor data on using the strain gauges. I have one with the bending loads, the bending stresses of on the rocket's fuselage are. So yeah, I mean, that's kind of all I have to say about that. I think after this, we could probably hop into the actual CDR itself. Carmen's going to go to the next slide. Cool. Aerostructure, do you guys want to take it off from here?
Yeah, just because the nose cone is kind of Adam's baby now, and he wasn't able to make it, he actually made a video of him doing the presentation, and I'll take any questions for the nose cone, and I'll forward them to him if I can answer them myself. I can't hear any sound.
You guys can't hear anything?
Do you hear something?
No.
I hear stuff. Okay.
Okay.
You have to like specifically share sound. I think there's a setting.
Will this work?
Action.
Yep, we're good.
Okay, hello everyone. This is Adam speaking, and welcome to the nose cone CDR part. Anyway, so starting, let's go. Design goals. Design an aerodynamically good performing nose cone for the specified flight regime. Design a nose cone that will fit the MaGP-I and other components, and design a nose cone that can repeatedly be manufactured and documented well. So these are the things we're trying to accomplish this season. And the overview for this presentation is, or just some takeaways, I suppose. Subsonic flights tend to have shorter nose cones because skin friction dominates rather than wave pressure drag. And then cone shape that we're aiming for, something manufacturable, something that performs well, so low drag, and good use of space. Cool, so some background work. As before, this document is just being updated as we gain more knowledge and make more rockets. So yeah, this can be found on the drive if you just search nose cone geometric design. Anyways, in this document, we show the Mach regime versus performance versus nose cone shape. And then we fine tune it with RAS Aero 2. And there's a link on the drive. So general design for this nose cone is an elliptical shape with an 18-inch length, diameter of the fuselage portion that goes inside. It's 4.51 and an outer diameter 4.66. It's got a smaller fineness ratio than we usually see, about 5, because it's subsonic. So 3.8 is more common for the subsonic ones. Or sorry, it's lower than 5 is more common for subsonic. We don't need blunting because elliptical nose cones already have a rounded tip, so that's cool. And there is the equation that makes up the solid of revolution, which makes this shape. Yeah, so some identifying points. The fuselage transition is tangential, so it makes sanding and post-processing a bit easier. It just means that it matches up very smoothly with the fuselage as opposed to like a cone, which would be sort of sharp angle. It's naturally rounded, as I was saying, so no blunting. And we're not using a tip insert, only the fuselage interface edge insert. And I'll talk about that in a minute. So, as most of you know, manufacturing work has been going really well. The 1/3 scale nose cone has been super awesome. I've made 3 nose cones so far. Yeah, I think this is the first time we've successfully made a single layup, like single one-time layup and cure all at once to make one cone rather than doing sort of 2 layups, which is super exciting because it means we can manufacture them a lot quicker, which means we can push testing a lot faster. So yeah, 2 videos have been made following the process so far. And as I was saying, yeah, there's no tip insert for the last 2, and moving forward, we won't be using them. The fuselage insert was too thin to print this time, unfortunately, so I couldn't test with it. But the next few will be, the next few layups we'll be testing some different techniques as well, and just sort of playing around with different things. But anyways, there's the video links if you want to go watch it on your own time. Not time right now, but yeah, pretty fun learning experience. Okay, so manufacturing tools, there's a lot here, so I'm not gonna like go through everything super in detail, but I'll just run through it quick. We've got the 3D printed molds, which are here. They're annealed PLA. We've got the sanding jig here, which I talked about in the video a little bit, but basically, yeah, it's a sanding jig. Down here is the controls that I've implemented for it. So we've got low speed, high speed, on and off. Yeah, and this is good enough for full scale. Down here, we've got templates for cutting. For the full scale, what we'll need is some bigger sheets, obviously. But we'll probably do like laser cut, thick laser cut paper or cardboard or something like that, because the paper was just a bit flimsy on the corners. So yeah, and then this should say plungers and stuff. Sorry, yeah, the templates here. So this is an interesting point that I've learned coming along the way, is that this is the deformation plot of basically the unwrapping of the shape, like a half of a nose cone. So you can see stretching and compression, lots of sort of issues at the tip. So it makes the layup challenging when you're putting them into the molds. So these extra lines just show extra material that's needed. So you can tell it's kind of an art, I guess. And yeah, anyways, all this other stuff here are just plungers for helping lay up and do vacuum bagging and everything. And this is a soundproof box because my vacuum is loud. Okay, so future work. Planning on starting the next little layup next week, changing the cutouts. Yeah, I will keep you guys up to date on what I do and whatnot. Oops, don't go forward. Yeah, tip refinement. So I want to do sort of a plunger and a plug that goes in between the vacuum bag and the green cloth. But yeah, there's some sort of experiments I want to do. And then there's some issues with the bagging. It's problematic because it's such a small layup that the cloth like bunches up and you've got lots of like pleating, I think. So it just makes it hard. But I've got ideas to make it a bit better. Yeah, once the methods are tuned, CNC the molds at my grandpa's CNC at my grandpa's house. I should be able to do that within a month and a half. I already finished up the mini lathe. I'm working with Liam and the Fuselage boys to figure out some cutting techniques and whatever. Get a better vacuum. Yeah, a little guy can pull about 85 kilopascals, but I'd like about 100 kilopascals of vacuum. But yeah, for now, the little guy's good. We'll get to the big one later. Finish the oven assembly, hopefully within a month, and then practice full-size scale-ups. Sorry, full-size layouts. Hopefully have at least a couple done before the end of August. At least one done for July, I think. So yeah, and I think that's about it for Nosecone. Are there any questions?
Do you think the full scale will be easier because it'll be a bit bigger to do than the 1/3 scale?
Yeah, I think it will be a lot easier because it's really challenging to get any tools in there and the bagging and the vacuum and whatnot. So if you had a lot more sort of radial room for expansion and whatnot of the bag, or sort of like compression of the bagging, I think it would make it a lot easier.
For sure.
Yeah. Cool. Any other questions?
Does anyone have any Nosecone questions before I begin?
I have one quick one. If you go back a couple of slides, Carmen, I think there's some 3D printed like compliant spacer things. They were in that shot. Yeah, the gold and silver ones. I remember Adam made a post about them. Do we have 3D printers big enough to make those for the full-size Nosecone? Like, are they a critical part?
They're not very critical, okay. I don't think. I think it helps them get a slightly nicer surface finish, but I think with the bigger one, you'd be able to even stick your hand in, so you might not even need those.
Okay, yeah. Just wanted to make sure that you didn't need like a 30-inch print bed or something. But cool. That sounds like that's good.
One thing is that this whole process looks really good. I think he's definitely refined it, which is awesome. My one concern though would be the sanding lathe. Will we be able to scale it up to like a lathe in the shop? You know?
Yeah, he thinks we can, or it'll just be good enough to just do it on that little lathe.
For the full size one?
Yeah.
Okay.
Yeah.
We do also have a spin caster and a filament winder we can use.
That is a very good point.
I'm just going to note these before I begin.
Other than that, I think that process looks really good. Makes sense to me.
Yeah, no, it's been going pretty well, which is very nice. All right, guys, I'm just going to take a quick drink of water before we start the air brakes. Oh. So essentially, the function of the air brakes is to slow the rocket down using an algorithm so we can hit our 10,000 feet. And it also couples the upper and lower fuselage together. Another thing I forgot to mention on there is it'll allow us to, on this rocket, like they mentioned, get some data on how they actually perform in flight. That's not just theoretical. So it's mostly, or all aluminum except for the fasteners, post and plate design, and has a NEMA 23 stepper motor, which controls gear-driven flaps, which are the things that slow it down. Next slide, please. Perfect. So there's a photo of it. Looks pretty cool. There's 4 bulkheads attached to the fuselage. And then, yeah, stepper motor controls the gear drive system. For the electrical design, we have 2 A4988 stepper drivers wired in parallel, so we can bypass the current limit on them and get the full current to the motor. Those are located on a breakout board on the Avionics bay. And they're attached to the Raspberry Pi in Avionics. And then there's a separate battery supply in the Avionics bay, which, as you can see in the figure down there, that is actually what powers the motor. And then there is I'm not sure, you can't see it on there, but there's just a little rotary position sensor which provides position feedback to the flight computer. Next slide, please. Do you want to play that YouTube video, Carmen? I don't know if I'll mess up your full screen. It can just be small, that's fine. So there's breadboard, that's pre-parallel, but I've been running them in parallel now and it's been working good. So as you can see, it's pretty cool. I didn't put it in there, but the positions on that video were full, half, 3/4, quarter, done then, I think. So yeah, the stepper motor is working pretty well for us. And then testing and analysis. Some FEA was done in ANSYS using some of the bending data and other flight dynamics data. And our minimum safety factor is 4.0, which is pretty good. Due to the dual bulkhead design, tear out isn't a concern because we have lots of set screws. And then based on deformation and ANSYS, binding won't be a problem. And it was less than 1 millimeter in the direction of the bind. Next slide, please. Yeah, software-wise, this is where we have a lot of the work ahead. Connor and Ben have been working on it, but I have pretty good faith in them. So we're going to integrate the existing MATLAB code that the previous guys made and is semi-completed. We're going to change that to Python for the flight computer. And just a little way the algorithm works is it provides a target CD, coefficient of drag, to reach our goal apogee. And then a second part of it takes that CD and it gives us an angle for the air brakes. And then through that angle, we get a step for the stepper motor. And then that's communicated to the stepper motor through the flight computer. And this is pretty cool because it allows for minor real-time adjustments during flight. I talked to Connor. He said should be able to finish the software within the month. Next slide, please. Yeah, and then so for testing, one test I want to do is a load test. Just put some weights on the flaps and see if it can still open under load similar to that during flight. And I have a little 3D printed guy. I think I might refine this a little bit, but it works fairly well. And the tests have been working well so far with lightweight. And I just put weight on here. And I can do that at my house because I have everything here, and those should be done with full weight within the month. And then hardware in the loop test. Once the software is done, we would want to with what's it called? The past data and predicted data. Try and run some hardware in the loop tests and see as it goes through the whole process if it works, and make sure that works. So that'll obviously be done once the software is finished. And as I said, both of these tests do not require the school, which is nice. So we're not really waiting on anything for those. Next slide, please. So for future work, we have some manufacturing that should all be able to get done at UVic. Software-wise, we just have to solder up the breakout board and continue with the code and then conduct the tests. And that's kind of our timeline down there. And yeah, that's all I got. Any questions, guys? I'm not sure. I can't remember what their budget was. That Devin, you might be able to answer that a bit better as you've just seen the geometries and stuff.
It definitely wouldn't be easy. Like it's quite a complex assembly. So like with like time only dedicated to that, like after hours might be like a month of work potentially. Yeah, in their initial report too, I didn't
test impact, but their impact safety factor was slightly above 1, but so I think it was like 1.05. So they should, big asterisk, survive impact, but obviously I can't guarantee that. Any other questions? Perfect. I'll pass it off to Aaron.
Hey guys, Marin. I'll be talking about the fuselage. The slide here, you can see the main parameters. Main important things to note are that 75 thou thick. And the lower fuselage is quite, it's only around half the length or so of the upper fuselage, but they are all manufacturable in our manual. So to validate this, first we determine the expected loads, and then we find the composite properties, and then from there obtain the safety factor. To determine the expected loads, we need to determine the failure methods, and we analyze set screw tear out and compression and bending. Next slide, please. Set screw tear out and compression are fairly easy to analyze. There's simple equations with drag and thrust, as well as acceleration and the weight of the rocket. We analyze these at the recovery bulkhead due to parachute ejection, and at the thrust ring due to thrust. Bending is a bit more complicated, so I'll talk about that in the next couple of slides. You can go ahead. So essentially we do a bending analysis. It's a aerodynamic force analysis to determine the loads on the rocket during flight. And sort of summarize the whole process, we model it as an unsupported cylindrical beam. We cut the rocket at sections at each bulkhead, and this is because the subsystems, the masses of the subsystems are transferred to the fuselage through the bulkheads. From there, we can find the accelerations laterally and angularly of the rocket. As well, we'll have lift. So in the nose cone, the fuselage, and the fins, they'll act laterally on the rocket, and these all cause rotation. The main inputs here are center pressures. This is obtained through Aerolab, as well as the lift coefficients. It's highly dependent on the cab. So the center of gravities, moments of inertia, and the subsystem masses are all obtained through SolidWorks. So the output of here is only as good as all the cab. Next slide, please. I'm not going to get too into details here, but this is a force diagram. You have the center of gravity shown as the nose cone, lift, angular acceleration. The other lift surfaces are the boat tail and the fins. And so we have equations for both shear and moment, obtaining the lateral acceleration and the angular acceleration. Next slide. So this is just the sample section. We cut it at some arbitrary point along the rocket. In the second equation, that's the equation for shear. So acceleration and the lift in the upper portion of the section. In this case, it's the nose cone. And the bottom equation there is the equation for moment. We have three terms. The first one is a inertial term. Second one is the moment caused by the lift. The third one is the internal shear. So we, again, do this at every bulkhead, essentially. And you can see on the next slide, we obtain shear and bending moment along the rocket's axis. So the main things to note here, the maximum shear is around 133 newtons around the air brake bulkhead closest to the nose cone. And the bending moment's around 100 newton meters at the other end of the air brake, at the air brakes. As you can see, shear 0 across the center of gravity, which makes sense. Got some peaks around the MaGP-I and propulsion masses, as of course those are the most mass-intensive subsystems. And the data should be a bit more continuous in this, as well as at the very right, you can see shear should end at 0, but it doesn't in this case because that final point is at the thrust ring, not at the end of the boat tail. So it should go back to 0. Yeah, next slide. So we've been pretty limited in our manufacturing testing. So for the data that we do have, we have previous tear out data of around 1100 newtons to tear out one screw in a layer of in a 6-layer composite. I'll talk about this main concern here later when I get into the safety factors. So for our tests, we're going to do 2 main tests. One is, as I was saying, the tear out, and the next is the flexural testing. This is to get a flexural stress on the composites to provide a safety factor for bending. And we'll do this using a 3-point bend test once we get access to the university. Next slide. So using a pre-preg test plate that Nolan made, main thing to note is it wasn't under vacuum, so future dimensions and properties will be better. Converting that plate to our fuselage will require around 9 layers of pre-preg to get our 75 thou thickness. So we have 2 main plans for the makeup of this fuselage. One is pre-preg, which is our plan A. We estimate the mass to be around 1 kilogram. It'll be 9 to 10 layers. If this doesn't work, we'll go back to our wet layout. To obtain the same thickness, we have 9 layers of tech stream. We have all the material in hand. We know how to make it. It is less than ideal, of course, compared to pre-preg. Next slide. So most of our timeline relies on the oven. If it's completed in its estimated time and everything goes well, it should be done around the next month. And in this case, we won't need access to the school, so we'll be able to manufacture full fuselages not in the university, which would be great. If this isn't the case, then it'll all just depend on when we get access. With that said, we'll also not be able to do any other sort of tear out testing or wet layups. Next slide. So our main safety factors. Our set screw tear out. Propulsion at the propulsion bulkhead's looking pretty good, 3.87. Recovery bulkhead is our main concern. We only get a safety factor on 1.2. This is noting that the fact that recovery loads are might be lower, as well as this uses just a 6-layer composite. So we anticipate that this will be higher in reality once we fully test. Compression, we'll get around 2.73 megapascals of compressive stress. This isn't really we're not anticipating this to be a main failure method. And normally it wouldn't get to this stress. We'd encounter other ones first. So, but with that said, we are gonna look a bit more into this. With bending, converting the maximum bending moment to stress, and then using flexural stresses from previous compositions, we'll get a minimum safety factor of 3.5 if we were just using a 4-layer twill carbon fiber, and a 9.5 in 9.5 safety factor with the 9-layer tech stream. So again, we're not as concerned in bending. All the forces on the rocket are much lower compared to previous years, since only 10K. And our main concern remains to be at the recovery bulkhead due to ejection. Next slide, please. Okay, that was sort of it for fuselage. Claire, you can try to bring this one up, and then we can take questions after.
Yeah, so basically we're kind of tag teaming aero and flight dynamics for all the airframe stuff. Flight dynamics does loading, aerodynamic stuff. So I calculated all the aero loads. Basically using Aerolab, it'll spit out all your coefficients of drag and lift for each each piece of the airframe, like nose cone, fuselage, boat tail. And I found that at our maximum speed, max Q, that's basically your maximum loading, because drag and lift are a factor of velocity squared. And these are all the results. If you need the data for any reason, it's in that spreadsheet I've linked there. And yeah, just pretty simple force and like drag force and lift equations.
And that's it for the fuselage.
Any questions for the fuselage?
I just had a question about where you got that value for the load on the recovery bulkhead, because 900 newtons seems really, really low. Because I think we were testing, like, we're still kind of have preliminary numbers, but we were getting like maybe 1,500, 1,600 pounds.
Yeah, that was, or Claire, you might want to answer this one.
Yeah, I was working on them with that. I gave them 1640 pounds as the total load, but it's 900 per accessory.
Okay, that makes more sense. I was worried. I was like, oh man, this rocket is not going to survive.
Oh yeah, these are forces per set screw, so you just divide it by set screws.
Okay.
Yeah.
Perfect. Thanks.
One more question. You're using a lot of numbers from previous launches, and we haven't had antennas on the outside of the rocket in previous launches. Specifically, I'm looking at your 4-layer twill, 1-layer fiberglass numbers. Do you anticipate any of them changing given the difference in distribution of material, since there will be kind of a bump on one side?
Well, yeah, that's something we should test. We haven't really, worked together too much regarding antenna. So once we start making these, some of the tests that we are planning to do is with that antenna. So we'll talk to you about that. But again, the 4-layer twill, 1-layer fiberglass, this is a lot thinner than it would actually be, and so therefore, weaker versus our anticipated 8 or 9-layer. But we do definitely need to test bumps as well as with the strain gauge.
One more question. So if you have a layer or 2 layers of different materials, will there be any issues with different coefficients of expansion with temperature? Like, are you going to run into issues where it like cracks apart?
Oven wise, like, I think we're just going to do a only carbon fiber. And then we'd probably just do a wet layup for the 1 layer of fiberglass that has to go over it to cover the antenna.
Okay.
So that should be all right. And then I don't think the temperature differences will be too bad that it'll crack, but definitely something to consider, especially if it's cold lake in the winter.
Yeah, that's what I'm thinking. Like, if you go from a warm UVF building out to like 0 degrees, is it gonna?
Well, the estimate is 1.75 degrees Celsius per 1,000 feet of altitude on average. But if we run into any weather, then it might get a bit colder. So already you're looking at about 17 degrees difference between ground level and 10,000 feet, not including weather that may impact it. So if getting that much colder is going to have any issues, then that'd be something to look at.
Yeah, no, we'll definitely look at that one, because that's a really good point that I completely didn't think about. Thanks, guys. Aaron, I'm not really experienced with what we've done in the past.
How big is the hole, sorry?
It's 3/8.
3/8. That doesn't seem like it'd be too bad, especially if
I think we've had bigger cameras in the past, but something to think about again.
Plus, you guys are planning to like put a backing plate kind of thing behind the camera, so it's not like it's just an empty hole into the avionics bay.
For sure.
Yeah.
Thanks, guys. That's everything.
Okay. Before I start the fins, I just had another thing about the like change in temperature cracking the fuselage. The coefficients of thermal expansion for fiberglass and carbon fiber are both pretty similar. So there shouldn't be too many issues there. But yeah, definitely something to look into. Anyways, let's get started with the fins. The design should look pretty familiar to everybody. It's a very similar design that we used on HIAC 2 and that we plan to use for HIAC 3. The only main difference is that everything was designed to be manufactured in-house. So the fin foot will be made from 6061 aluminum angle iron stock from McMaster. There aren't too many sort of exotic looking curves on it. It'll be a lot easier to machine. As you can see in the bottom picture there, there's some pockets cut out as well to save machining time and weight. Yeah, and then the fin plate will be made in-house as well. It'll be a pre-preg layup. It's going to be pretty thick, probably 20 layers. We haven't done anything that thick before, but we don't see there being any problem with that. Should be all good. Next slide. Yeah, so testing. So in the past, we've had a couple problems testing our fins. The main reason being they were so overbuilt and so strong that we couldn't get any like results for deflection since our jigs were basically too weak and the plate was just incredibly strong. So we've been looking into that a little bit, trying to see if we can get some different jigs, but we've also shifted the majority of testing to sort of FEA and CFD. I'm not going to go into that. Claire will talk about it after. But yeah, as you can see, there's the 3 physical tests we still plan to do. It's sort of a backup plan testing method, but we do hope to still get 3 safety factors from that. Yeah, and then in the top right is just a quick timeline, how we plan to do everything. But yeah, that's everything for Aerostructure side of the fins.
Hi. So onto flight dynamics side. So first, we got the sizing. So basically, if you don't know, the fins are responsible for stabilizing the rocket. They basically bring the center of pressure aft. So in general, increasing stability is increasing drag. So basically, the sizing is kind of balancing performance versus stability. So this year, we did them kind of change the fins as we needed with the trajectory analysis to avoid adding just dead weight to the rocket. We did do a little kind of experiment in RAS Aero. One of the flight dynamics members, Karnika, helped me with this. So the bottom axis there is inches, and then y-axis there is altitude. And basically we found the center of pressure, found how much ballast we needed, and tested how like the apogee changes. Basically, as expected, any increase in area is increase in drag, and the span has the greatest effect on drag and stability. So that is kind of the key parameter to watch out for. So you go to the next slide. So I just have some pictures to show you guys what the actual, parameters mean. And the fins we settled on have a 10-inch root chord and 4 1/4 inch span. Those are kind of the key parameters. If you guys want to read through the rest, you can. And 0.17 inches thick, as Aero said. Yeah, so they are smaller than the HIAC 3 fins. So they should be less mass, less drag, but they're the size we need for our stability. And so if you move on to the next slide. So yes, Flight Dynamics is in charge of the structural analysis, like failure analysis of the fins, theoretically at least. So we're kind of concerned with like the fin under like bending load from lift and also with fin flutter. So the first thing we did was just run a really simple FEA just with the estimated lift as and drag as a point load in the center of the fin, just as kind of a sanity check, because you don't want to just dive right into FSI and have some kind of super whack results. And that gave us, I don't have the results because they're not like super accurate to what's actually going to happen, but pretty low, like a couple of megapascals. Next, we did a one-way static FSI, which basically means do a CFD sim, get a pressure plot, put that into FEA, get a stress plot at Mach 1.2 and 1 degree angle of attack, basically wider angle of attack, higher lift loads. But it seems like we should be expecting like a narrow angle of attack from like previous work and research. Because we don't know material properties, I just used the carbon fiber prepeg option in ANSYS. And we modeled it with all the bolts. So clearance holes, any clearance holes have a friction contact. The fin has a friction contact on the foot. And the mounting holes are fixed to the ground. And they have a 1250 Newton preload. It was kind of based on Simon's previous work. It's about half of the kind of, I think, listed like clamping preload. But I also tried some higher numbers and they didn't really affect the stress, so we could change that if we needed to. And the fin foot was fixed so that it can only deform like, or like move axially along the rocket. And two-way FSI was not performed, had a lot of difficulties with it, and the loads were so low that I just didn't think it was really worth it that much. If you go to the next slide. So here are the results. Top left corner is the stress plot. It's very low stress, 0.13 megapascals on aluminum is nothing really. And on below that, we have the deformation plot. So that's kind of what we would expect. The tip of the fin, since it's based the lift acts normal, it's basically bending, it deforms the most. And this picture in the bottom right here is the pressure plot from CFD. So the maximum pressure there is 88 kilopascals. So the stress value kind of makes sense in my opinion. And also just calculated the dynamic pressure, which is just 1/2 density times velocity squared, and that's 75 kilopascals, just to kind of make sense of this plot, make sure it's kind of the right magnitude, I guess. Yeah, so I guess next slide. So the second failure mode we're concerned about is fin flutter. It's basically a vibrational failure mode. At certain air speeds, the fin can kind of just start to like flutter, and we suspect that's been a problem in the past. So the two main factors that affect this are the fin span, so like how long it protrudes from the fuselage, and the shear modulus. So there's been a lot of previous work on this. There is this NACA paper that basically lays out all these equations you need to calculate the flutter velocity. The issue with this is you kind of need the shear modulus to determine thickness, and we don't have testing, so we don't have a shear modulus. Talking with Aero, we kind of based it on 10 gigapascals, which is half of the Hayek 2 and 3 rockets. And based on that shear modulus, we have a safety factor of 1.45 for that 0.17 inch thickness. And I think that's all I have for fins. There's Aerostructure budget.
I also didn't know. I just read the thing. You don't need to have budgets on the slides. So, yeah. Let's skip that.
One question for Claire. You used Mach 1.2 for the fins. Why? I mean, it's good to have a higher number, but since the rocket isn't going to be achieving this even Mach 1, that seems like a lot.
At the time when I did that simulation, that was our top speed, actually. It is slightly lower now, but we are reaching just above supersonic speeds.
Cool. Okay, thanks.
No worries.
Yeah, I just want to add, if you guys have any other questions or whatever, just send me or anyone who presented a message on Slack, and we can further discuss there. Thanks.
Okay, so JJ and I will be talking about all these elements of our recovery system, starting with the bulkhead. So next slide, please.
There's the, yeah. Okay, so here is the recovery bulkhead. Quick specs, 4.5-inch diameter, made out of 1/2-inch thick 6061 T6 aluminum, and all of the mass that includes like high volts, fasteners, and everything. Total mass is 1 pound. That doesn't include things like the shock cords and stuff, though. This is just for the bulkhead. For the bulkhead design, same as usual. If you've been to a Hayek 3, FDR, or whatever, you know about Taco Link. It's the usual setup. We've only made a few minor changes to that release mechanism. And one of them was that we shrank the size of the slot there just to keep it away from the radial holes. And yeah, that's actually about it for Taco Link. Everything else is the same as it was before. And then for the drogue ejection, we've originally, I think in the PDR, we had black powder cups that mounted to the bulkhead. And so they were like a little machined aluminum cup that would sit mounted on top of the bulkhead, and that would be filled with black powder. And then that would be ignited, and that would blow off the nose cone and eject the drogue parachute. But we did a little bit more research, and we figured that we can actually just make the pocket right into the bulkhead and then have a little cap that sits on top. So you can see that in the bottom of the bulkhead there. So that just saves us a little bit of space. And then, one other small design change is instead of using a 8 contact terminal block on the back of the bulkhead, we are now using a 6 contact terminal block. And that's just because we made the slot smaller, so we can make the terminal block smaller. And if you go back one slide, you can see that a little bit better with that animated video. So you can see there on the back that we've dropped down to a 6 terminal block. And so next slide, and the one beyond that as well. So for the Taco Link, we did a bit of analysis on the drogue parachute. So we've had issues with this in the past, getting like a good number for how much load will be on the drogue parachute. And in turn, that load is distributed to the Taco Link. And so this time I took a bit of a different approach, and I assumed that the shock cords are rigid and that the drogue parachute is fully inflated when the load is applied to it. So that's the worst case scenario because it's going to provide the most drag. And sort of the key difference in this type of simulation is that the load is actually the drag load on the parachute, as opposed to, you know, like the shockward stretching and things like that. So what we assume is that the parachute is deployed and the rocket falls and the shockwards go tight. They are completely rigid and elastic, and the moment the shockwards go tight, the rocket fuselage is moving at a certain velocity and the drogue parachute is moving at that same velocity. And then using that velocity, we can calculate the drag. So after talking with Claire, we got our horizontal velocity at apogee, and then we add that to the velocity gained by falling back to the Earth from apogee. And we came out with a number of 255 pounds of loading. And that is sort of a worst case scenario where the drogue parachute isn't deployed right at apogee. It's actually deployed 50 meters after apogee. So just in case things go a little bit haywire with the avionics system or something, and the parachutes deploy late, the rockets picked up some speed, we still only get a number of 255 pounds. So as part of our simulation, we applied that load to the Talk-Link tether, which is that yellow thing there, and you can kind of see, you know, forces pull on the side. And using SolidWorks, we got a safety factor of 5.9. So in the future, we want to also run this with ANSYS, but never really used ANSYS that much, so I just did it in SolidWorks. Next slide. And then I'll let Arturo take over here, and then I think Claire will also touch on this.
Yeah, so for this is the bulkhead analysis using the load from the main parachute. So this is something that we had a lot of trouble calculating a right estimate. And so our best estimate so far is 1,640 pound load distributed between the two eye bolts. And we got this estimate from a MATLAB script that Nick wrote, but we're still having some issues on getting that right. But based on a previous estimate that was the closest thing that matched our now current estimate, but we expect that that is an extremely high estimate. So once we get it right, it'll be a lot safer, I guess, than this one. So it's good that we're testing on a very high estimate. So I'll let Claire talk about the FEA.
Sure. Yeah, so I did the FEA in ANSYS. I included the bulkhead, the pins, and the bushings. For sake of like not having a billion contacts in ANSYS, I did not model any of those like terminal blocks and stuff under, because I don't think they should affect it too much. Basically bonded the bushings to the bulkhead, frictional support between the pins and the bushings, and all the radial holes have like a fixed cylindrical support. The loads, so the eye bolts are threaded, so the loads are applied to those hole faces. And the load is split like half between each eye bolt. And then I highly refined the mesh around each of the eye bolt holes and those adjacent radial holes. I came out with a max stress of 193 megapascals. It's at those like adjacent radial holes you can kind of see in the bottom right picture. And this little picture in the center kind of shows the mesh and where that high stress area is. I ran it at a bunch of different mesh sizes. That's what this graph is showing. So smaller mesh size, you're getting a higher stress. And that's the mesh size, sorry, of just the radial hole. So I refined it down to 0.5 millimeter, I believe. And that gives a safety factor of 1.4.
Yeah, so the future work for the this aspect of the bulkhead is just to revise the calculations to narrow it down to a better estimate, and then just perform physical testing, because even if we get a right estimate, with the physical testing, we'll know for sure just how strong the bulkhead is. So we can move on to the next slide, please.
Okay, so I can talk about this a little bit. In terms of talk length, the testing that we've done so far is a test under the load of the drogue. So if you remember, rocket's coming down and the drogue is deployed. The thing that holds the drogue parachute to the rocket is the talker link. And so the mass, or the load, I guess, on the talker link is just going to be the weight of the rocket. So we tested at twice the weight of HIAC 3 because we were testing HIAC 3's bulkhead, which uses the same talker link system. And it was successfully able to deploy the drogue parachute at 1.5 times the load. And that was using 0.3 grams of black powder. And we're planning to do future tests once we have the 10K rocket talker link manufactured. We have also tested the low pressure ignition of black powder, and that was done by Paco. He created a vacuum chamber and was able to successfully ignite black powder at 10,000 foot pressures. So we're not worried about that. In the future, we're planning to do some tests with the MTI machine at the university, and that will be loading from the main parachute and then also loading from the drogue parachute, just to double check that everything sort of doesn't fall apart. And then we also want to do a realistic test where we take the mass of the rocket, attach the main parachute, and also have load cells in line with the shock cords and throw it off a building or something, and finally get a number that we can trust for the main parachute. But in order to do that, we need access to the rocket room, the MTI machine, and also all the avionics equipment to do sort of the vacuum chamber, like low pressure parachute deployment stuff. Next slide.
So the shock cords, basically they just attach the parachute shroud lines to the recovery bulkhead. And there are there's one for each parachute. And so basically, we've been having some issues as well with getting the right calculations and just some good sources on the sizing of the shock cords. The strength will depend on the load once we get a better estimate for the load. And JJ is going to talk about that in a second. But in terms of length, we haven't gotten too many great sources, but basically we just want to avoid zippering, which is basically when the parachutes are deployed. If you say this is the fuselage, when it gets deployed, it's going to have some horizontal velocity, and so the cords are going to shoot out, and because of the drag on the parachutes, they're going to fly backwards. And so basically zippering is just when it tears along the fuselage. And so in order to prevent that, you need 4 to 5 times the length of the fuselage, just to give it enough time to slow down. And so for the 10K rocket, that would mean 10-yard cords for each parachute. So one for the drogue chute and one for the main chute. Zippering mainly occurs with the drogue chute because that's when the rocket is the least stable, I guess. Once the drogue chute stabilizes it, it's not as much of a concern. So there is a possibility that we could maybe bring that number down for the main chute, but for now, just with the research that we've done, 10 yards is enough. And I'll let JJ talk about the material.
Yeah, not really too much to say, just that based on our research, Kevlar, while it is stronger, it's much less elastic than nylon. So, like in model rockets, they use elastics because the parachute deploys and the elastics just stretch and absorb all that energy. So we want to sort of replicate that a little bit. So rather than using Kevlar, where it's like no absorption at all or very little absorption, we'll use nylon instead. and as a plus nylon is also cheaper. So, but again, that depends on the load that we measure when we do our actual test with load cells and the bulkhead and the weight of the rocket and the parachute. So we may find that we have to up it to Kevlar if our loads are so high that you can't get nylon shock cords that are strong enough. But yeah, next slide.
So the testing for the parachutes is not too complicated. The big thing, or the main thing, is making sure that we complete, that we finish sewing the parachutes. And so that's going to take probably a couple of weeks. That's the hardest thing. And then after that, we have 3 tests planned for the parachutes. And they're fairly simple. One of them, the shroud line load stitch test, does require the MTI machine. So on top of requiring the university for the materials and the sewing machine, once we finish that, we're going to need the MTI machine. So it looks like we might have to wait for the university to open before we begin the parachute testing. Next slide, please. Okay, so MaGP-I. I'm just gonna go over it briefly before I go into the software, which is the main thing I want to talk about. So MaGP-I, which is a machine-guided parafoil, guides the nose cone to whichever location we want after apogee separation. So unlike previous years, the nose cone is actually going to fully separate from the fuselage, and it's going to steer itself using, or it's going to steer the parafoil using stepper motors controlled by an Arduino Nano flight computer using GPS. So next slide, please. The software was written by a previous student, River, but I've looked over it and I've verified it and written some pretty in-depth documentation. So if you guys want to look over that and just make sure everything's fine, you can do that. But basically, we just wanted to make sure that there were no issues with the software, and we wanted to make sure that we knew all the launch-specific parameters that we had to change for flight. And so that includes things like coordinates, altitude, the number of circles that it's going to perform as it descends, things like that. And so using data from a previous test on the parafoil and a spreadsheet that I made, we came to a total of 17 circles that it's going to make as it descends, which would take about 40 minutes. And that might be an issue. I believe we've contacted Adam about that to see if it is an issue. If it's not, then we have some future work and testing. So I go more in depth about that in the next slide. So next slide, please. So testing for MaGP-I, as I mentioned, we've already completed, or some other members have already completed a parafoil glide test, which gave us information, some pretty useful information on the steady state vertical velocity. And now all that's left is just making sure that the software and hardware works well together, and just testing all of that. So we're going to use a MATLAB script that River wrote as well. And that, so the MATLAB script basically just inputs a bunch of values, and then it simulates the flight. And so with that, we're able to test the software, since doing or performing a high altitude drop test to test everything is not very feasible. And then on top of that, we're also gonna do a nose cone and parafoil ejection test just to make sure that that MaGP-I won't break or anything during ejection. And so that's going to go along with a full-scale nose cone ejection test that we have planned. And so basically the only equipment we need for that is MaGP-I, because we need all the sensors for the simulation. And so for that, we need, again, access to the university. So it might take a while for that testing to be, for that test to be completed. Next slide, please.
All right. So I've already talked about this in the PDR, so I'll just whip through it really quick. This rocket is going to have strain gauges embedded in it. We're going to be running the wires inside the fuselage, and then we'll have contacts on the inside of the fuselage that will mate with a bulkhead with some copper spring contacts on it. We'll be having 12 strain sensors on the rocket, using 12 amplifiers to convert the signals from those into digital and then sending those to the flight computer. And the mass of that is 0.55 pounds. Next slide. So we have finished our PCB. We've sort of had reviews and need to give it one more once over, and then we'll send it away for printing. So this PCB features 12 HX711 analog to digital converters, and they're 22-bit, so they give us a really, really high resolution. They also do 80 hertz sampling, which is relatively quick. And we also now have a low noise power supply, the LT3042, which will be providing very, very clean, stable power to our strain gauges, so that we're not reading the noise in the voltage supplied to them, because that would mess up all of our data. In order to manufacture this PCB, we need a reflow oven or the rocket room's toaster oven. We also need a soldering iron, fume evacuation if we're doing soldering inside. And then obviously we need access to UVIC for the rocketry room. Next slide. So we've had a couple small changes since the PDR, and that's basically where the mounting of the strain gauge bulkhead is. So previously it was on its own, but now strain gauge bulkhead is the thing that's screwed into the fuselage, and then the avionics bay mounts to that. So same as before, we have copper contacts that are embedded into the fuselage, and copper spring contacts that mate with those. And then in order to sort of force the contacts against the copper pads, we have a clamping plate that squishes them together. And yeah, like I said, the biggest change is that the avionics bay is now mounted to the strain gauge bulkhead. And the reason for that is we ran into issues with wiring. Basically, it wasn't possible to assemble everything if they were two separate components. So next slide. Yeah, and then like before, we kind of showed this off last time, but this whole project was a huge software ordeal, and one of the big parts was getting visual display of the strain gauge data. So you can see here we've sort of fleshed out the software even more. We've got grids that show the altitude of the rocket as it ascends. Also some data on the side there if you want, you know, like tableized numbers instead of just like colors and things like that. Added a bunch of other cool features to it that won't really go into detail here. But yeah, it's coming along really well. And I actually have another piece of the software that I want to demonstrate live. So if I can share my screen here, Carmen, and I'll show what's happening there. Thank you. Okay. So one of the big, or something that we haven't really shown before, is the ground station. So basically we have a whole bunch of graphs here that will display like altitude, gyroscopic data, things like that. So this is kind of like a more visual version of the ground station that Avionics has. So this is kind of like an addition to their system already. And we also have support for .rocket files. So we can have different files in here, different rockets, different CAD. So I've created one modeled after the 10K rocket. So this was using 10K's fuselage and things like that. So this is an accurate representation of that. And I've modified it so that it actually has 2 strain gauge sensors, which I have hooked up to a piece of metal sitting beside me here, as well as a gyroscope. So if you look at my camera while I'm doing this, I have a breadboard here with an accelerometer on it. You can see as I spin it around and move it, it moves on screen. And then also it has strain gauges built into the rod. So if you see if I flex the rod, one side is in compression, one side is in tension. And then if I bend it the other way, one side is in compression, one side is in tension. So this is what we'll get from the actual rocket, except with 12 sections instead of just 2. So that's sort of like one of the big improvements that we've made since the PDR. So I will let you take it back, Carmen. And next slide. Okay, I'll pass it back over to Arturo.
Yeah, so the timeline is going to be very tight. As you might have seen or might have noticed, all of our testing requires manufactured parts or access to the university. So I talked to Devin and he gave me an estimate of about 2.5 weeks for manufacturing. So assuming we're able to start manufacturing once we get back to the university, and then assuming that we're also going to start making the parachutes right away as soon as we get to the university, then testing might have to begin probably a week or so into that, once we have enough components to start that. And because we do have a lot of tests, it might take us 5 weeks if we complete 2 tests per weekend, which gets us right up to the beginning of October. So it is pretty tight for a competition. We might need some help from other subsystems to complete these tests. Otherwise, yeah, we're going to be very tight on time if the competition is in October. That might be an issue. So are there any questions about anything?
Yeah, Chris might bring this up with the JJ later, but I'm concerned about the size of the wire pass-throughs on the sides of the strain gauge bulkhead for the wires from Black Box. They look very small and like they'd be kind of a hassle to deal with when actually putting stuff together in practice.
Okay.
Yeah.
It might be tricky to make them too much bigger. But yeah, thanks for bringing it to my attention. I'll make a note of it here, and then I'll talk with Chris. Okay, sounds good. And one question, will there be connectors that need to pass through, or can we just have the wire with the connector already dangling down? And then, like, I'm wondering, do I need to cut out big enough that you could push a connector through it? Okay. Perfect.
I'd like to clarify something as well. On your first slide, you say that the black powder charges are connected to the flight computer. They most certainly are not. The altimeter systems are completely independent, so that way we can make sure that no other fault has any impact on them. So each altimeter runs its own power system, its own check of altitude. We'll be covering that more in avionics, but
that was, yeah, sorry. I always call it the flight computer, but I mean it, the avionics bay, I guess. The wires run to the avionics bay and connect to the altimeters,
yes,
I guess
okay.
is what you're saying. Okay.
Cool. Yes, I just want to make sure that was clear. Good.
Yeah.
That 2.5 week manufacturing period, is that based on like if we manufacture nothing but recovery in those 2.5 weeks? Or is that accounting for all the other manufacturing projects that are probably going to be happening as well at the same time?
I can speak on that. And that is assuming that we'll all be manufacturing like everything at the same time. Obviously, we have a lot of parts that are very similar, i.e. the bulkheads all are, well, plates are cylindrical plates. And so a lot of they have very specialized processes for making those radial holes. And so to streamline the process of making so many, it's easiest to make them all kind of at the same time. Because using it's called like a dividing head to break up the rotation of the disc on the mill to make all of those holes. It's time consuming to set up and tear down. So trying to do as many as we can in one like sitting is ideal. So I guess that 2.5 weeks does account for everyone or all manufacturing.
Thanks, Evan, for clearing that up. Are there any other questions or concerns? That'll be very helpful for us.
Why does the parachute sewing need access to UVic? You just need the sewing machine, right?
Yeah, I think, well, mainly we just need access to the materials, which happen to be
okay.
It's also partly about space too. Like we just need a big working area. Like the parachute's huge, right? And it's like a little bit unfair, I guess, to dump that on somebody's house, especially if you want to have. We need power for the sewing machine, so you're limited in that respect. I guess
the
so,
cutting, you'll need a big table
extension
cord that could be
cord.
done outside, but then everything else, you just need the extension cord for the sewing machine and a table because it's nice to have the foot under your foot.
Yeah, that's worth considering.
I actually have the sewing machine and the parachute. I think I said I was gonna make it, and I still can. However, I did see one of your tests was testing the stitches. I don't know if you want me to actually start making a parachute or making a whole bunch of test pieces for you guys to use in MPI.
We wanted to do test pieces first.
Okay.
And then, so actually, I guess we still need access to the university then before we can begin manufacturing.
That's right. I didn't want to start. I cut the stuff out, but I don't want to start sewing.
Right. Yeah, sorry, I forgot you had it, Carmen.
I'll talk to Arturo later about what the test pieces will look like, and then
sounds good.
Get into school, we can start right away.
Okay, thanks. Yeah, mainly for the parachutes, it might be good to start making the actual parachutes. Although, if we do that before the testing and then the testing results aren't very nice, we might run into some issues because I guess just the university access would be mainly for the MTI machine, and for that we do need access. So that will be sort of an issue. I guess that's the main.
Sorry to cut you off there. One thing I'd just like to add is I don't know if any other subsystems have to use the MTI machine, but I know Aero does. So, depending on university access, whether we get in early or not, if we could try and coordinate that might be useful. Just less time on it, and kind of do all our tests at once.
Yeah, I'll send you a message.
Yeah,
and,
for sure. Thanks.
One more slight concern. With your testing timeline, have you accounted for the fact that some of the things being tested last are the ones where if the test fails, it will take the longest to try another method? Because some of these look like they're being done earlier, possibly because you haven't had things manufactured yet, which I understand, but some of them could possibly be moved earlier so you have more time to remake things if anything isn't what you expect.
Yeah, we mainly, but I based it off of just having 2 tests per weekend. And so, just doing it sort of in a line. I try to put the full scale tests at the end because those are more like just making sure that everything works rather than tests to get data or any values that we need. And so, yeah, because we have so many tests, we're not really able to move things unless we get help from other subsystems, which is probably very necessary because, yeah, like you said, if the competition is in October, realistically finishing tests that same month won't be. We might run into a lot of issues with that. So we can look into possibly moving some of them. I can talk to some other people, see if or if any of you want to help out with any test, you can talk to me and we can figure something out just to make this a little easier.
Absolutely. We want to get them hooked on rocketry early, okay?
Yeah. For sure. We'll just have to make sure everything's safe.
Come play with rockets. We make things go boom.
For sure. Yeah, that would be great. Yeah, let me know more about that on Slack. Anything else? Okay. Thanks, everyone.
All right, everyone. I will be presenting for Propulsion. Quick agenda. I'll just go over the propulsion system function. Whether we go into the CAD is kind of dependent on how complicated the integration seems to be. I don't think it's pretty self-explanatory, so it may not be worthwhile. But after that, like subassembly or go through each subassembly, and then talk about the assembly of our system on launch day or just before, and then some timeline testing. And I made a budget, but there's no need for that. So next slide. So the purpose of the propulsion system is to integrate our Cicerone Technologies Pro 98 motor into the lower fuselage, as well as retain said motor during recovery. And so you can see we have the propulsion bulkhead, centering ring, the motor itself, the fin cage, thrust ring, and launch lugs as the main components or subassemblies. And the total wet mass is almost 7 kilograms. Next slide. So the propulsion bulkhead keeps the motor in place during recovery chute deployment. Unlike previous rockets, I know it was intended to be a backup for thrust transfer compared to the thrust ring, which we'll get into later. However, I feel like talking to Morgan, we kind of determined that if we are bottoming out on the propulsion bulkhead before we're bottoming, and something with the thrust ring is not working out, then we probably have bigger problems. But we can talk more about that in the thrust ring section. So as you can see, it's just bulkheads made out of aluminum. It's also the lower bulkhead for the air brakes. And so it's just an aluminum disc with 12 set screws. That's a 3/8 by 16 hex bolt attaching to the extension post that was added for the extension of the lower fuselage. And then, basically making a big screw. We have some threaded rod on the end. And then the required validation for this component, the bulkhead itself, is just loads under main chute deployment. And just for fun, we did the max air brakes load at full extension. Next slide. Okay, so this is the analysis done on the bulkhead. This is all in SolidWorks FEA. And so for main chute deployment, we just simulated the load applied by the hex bolt holding the motor with its burnout mass of almost 3 kilograms. And so, like JJ and Arturo talked about, we don't really have any recovery deceleration data. And so we went with the worst case of what our electronics are rated for, which is 25 Gs, which was a load of 734 newtons, and the safety factor on the bulkhead was 4.6, or the minimum safety factor. And then also on the top of the bulkhead are those the three post landings for the air brakes with a 129 newtons of load, and we had a minimum safety factor of 80. So we're looking pretty good there. So our fasteners also just some kind of, doing some, what is the word? We just want to do our due diligence and check the shear and tensile safety factors on some of our fasteners. And so the calculating the minimum thread engagement on that large hex bolt, and the tensile safety factor, both very high, looking very good for recovery loads. And like I said, the set screw shear is also around 30, so pretty looking pretty good there. And that was only for the recovery or main chute deployment, and so air brakes load was less than that. So we didn't do any analysis there. Next slide. Now the centering ring. So the centering ring locates the motor radially during assembly. This is our fun 25% infill PLA version. And its features include being lightweight at only 36 grams. And there's no validation required for this guy, just for locating during assembly. Next slide. Moving on to the fin cage. So the fin cage locates so where the centering ring was at the front of the motor, the fin cage locates at the back of the motor. It also fixes the fins to the rocket. So some of the features include unidirectional weave carbon fiber posts. That was what was selected for the HIAC 3 version, which was the design was kind of transferred over here. I don't know, and those are available from McMaster. I'm not sure, or I don't know too much about composites. And I don't know if there is going to be much of a difference between unidirectional versus like cross-hatched carbon fiber posts. But that's what was in the CAD. And those are connected with those expanding aluminum inserts to replace the initially used aluminum posts from previous years. And so the required validation was thread tear out for the fins on each ring, and then bend testing on the carbon posts. Next slide. So for what analysis was done was pretty crude, just a pretty worst case scenario bending moment or sorry, moment arm on the fins for fin lift or for lift force, and just to calculate the tensile safety factor on that top screw. Again, over 30, so fine there. In terms of the bending of the fin cage itself, no simulations were able to be performed because there's so many components interfacing with the fin rings connected to those posts or interfacing directly with the motor casing, and then being held together by the fuselage, as well as the I guess the diameter bottom of the fin feet. There's just too much interacting to have a relatively accurate simulation, and so that all that bending and determining whether the load will be, or any load on the fins will be transferred to the carbon posts, will have to be done or validated with physical testing. Next slide. So moving on to the thrust ring. The thrust ring serves as the base of the fin cage, as you may have noticed, and it also transfers thrust through the bottom of the fuselage. And so also aluminum, 12 632 set screws, and the only required validation was the motor's thrust transfer. So what the thrust coming from the back enclosure of the motor. So that's in the next slide. For another SolidWorks FEA, so that loading was just placed on the interface between the back forward or the back motor enclosure and the thrust ring, just on the back face, with a thrust of 2,952 newtons. We had a minimum safety factor of 4.7. And so worst case fastener calculations, or if for some reason that we bottomed out on the set screws before the lip of the thrust ring on the bottom of the fuselage, we got a set screw shear factor of safety of about 3.3 per screw. Yeah, next slide. So quick little diagram about assembly. How everything goes together is obviously important, but so it can be broken up into two initial stages where we assemble the motor all together first, and then applying Loctite to that threaded rod, we can bottom it out on the the front enclosure of our motor, and we use you can use two nuts to basically make like a bolt and screw that in all the way, and then basically applying putting on the centering ring, more Loctite for the other end of the threaded rod, and then we can use a pipe wrench to basically bottom out the extension post onto the front enclosure. The fin cage can then slide onto it doesn't slide over the motor. We actually install it first, making sure the thrust ring bottoms out on the bottom of the fuselage, and then we install the propulsion bulkhead above the fin cage, threading the set screws into the fuselage, and then finally sliding the motor and extension post in. We can simply just tighten down the hex bolt at the top of the bulkhead, cinching everything together and completing assembly. So next slide. So manufacturing requirements. All the parts that need to be machined are the bulkhead, extension post, fin cage, and the fin cage and thrust ring. And these are all the requirements. Like most of this, I know in past years we have just purchased like a large piece of aluminum round, and then just like taken slices off for each bulkhead. And so that is that kind of follows suit for the propulsion bulkhead, the fin cage, fin rings, and the thrust ring, and then other simpler operations like the extension post, and the those plane weave carbon rods can just be taken to length, and don't need much else. Moving on to the timeline, you can see we start with purchasing, and so obviously we have to order the motor from Sunward Hobbies over in Ontario, and so typically we order the hardware, so the all the both the back and front enclosures and the motor casing, and so first, and then so we can have everything assembled and meet the motor in competition or at competition. And so we can order the hardware right after the design freeze. So this is just set for the end of June. And that's the casing. And then we can order the motor itself at the beginning of August. And so that's so we can receive the hardware right at the beginning of September. And then the motor right at the beginning, the motor would arrive at the partner university, who can hold the motor legally at the beginning of October. And both of those dates have been confirmed by Sunward Hobbies, which is great. Receiving the hardware right at the beginning of September means we can go right into manufacturing. And that's allotted, I think that looks like 2 weeks on the for just the bulkhead, fin cage, and thrust ring. And then as soon as we're done manufacturing, moving into testing, right there, those are 1 week and 2 week increments for the bulkhead and fin cage. But the tests will only take a day. But that's accounting for like prep. Or in terms of making sure our testing plans are ready, and then acquiring all the materials beforehand. And then we plan to have assembly rehearsals up until competition, or up until like 2 weeks before competition. Next slide. Yeah, so I feel like testing probably should have been before the timeline. Either way, the testing, we're following the testing procedures that were done for HIAC 3, or were supposed to be done for HIAC 3, for the bulkhead and the fin cage. And so just like everybody else, you're using the one of these testing machines. I believe either the MTS machine in the machine shop or the MTI machine somewhere else in the building or in ELW will work for exerting the recovery loading on the bulkhead. And to summarize the testing procedure, we're just going to exert that loading and then measure for any deformation. We have no moving parts in the propulsion side of things, so deformation is less important because there is nothing to bind. However, we obviously want to see if our simulations are consistent with what we're detecting from those tests. As I mentioned, for the fin cage, not too much we can do in terms of simulation, but we hope to make up some mock fins out of aluminum in order to measure any deformation in the assembly, whether that happens in the carbon rods or that all of that load is taken up by the fin feet. And yeah, that'll be done with the drag and lift forces applied. I believe the plan is to again, like use a kind of worst case point load for both of those tests. Next two slides are both budget slides, which again, didn't know, didn't need to be there. So we can just skip those and go straight to the question and feedback period. So do you have any questions?
One just thing for you to note, you mentioned you didn't know what loads to expect. We have data from a few of the previous 10K rockets, I think MVP-1, 2, and Skookum-1. So you can use data from those if you're looking for more specific expected loads. 25 Gs is what we spec the electronics for, because it was either that or go significantly below expected loads. So it's still higher than needed, but if you're looking for more accurate data, it's in the Avionics folder.
Okay, great, thank you. Yeah, that was JJ and I's solution to not having any expected deceleration for this rocket, but yeah, I hope deceleration is less than 25 Gs. But thank you.
It has been every time previous. I just looked and we were looking at 10 Gs and 13 Gs for Skookum-1 and MVP-2. So
okay, cool.
Well within.
Great, thank you. I'll just write that down. Any other questions?
Yeah, if the safety factor against failure on the propulsion bulkhead set screws is so high, would you consider maybe reducing the number of set screws from 12 to maybe 6 just to reduce how many machining operations you have to do?
Yeah, that's a good point. Drilling and tapping all those holes is not super. It is not going to sound super. It doesn't sound super fun. So yeah. That's and that was just using the fastener design spreadsheet in the recovery section, and so whether that is a good resource or a trustworthy resource or not, I'm not sure. I may have been using it completely wrong. However, so if anyone knows how to use it better than me, please reach out. But if that's the case, we can definitely reduce the number of set screws because, oh boy, yeah, I didn't actually consider that.
Yep.
On that point, the number of test screws is also determined by the tear out strength of the carbon fiber.
Oh, yes.
So until we know that exact data, it's not well changing.
Okay, yeah. Forgot about that. Yeah. Okay, just gonna write that down really quick. And any other questions about the propulsion subsystem? Cool. Okay. Thank you for listening to my presentation. You may continue.
Would we like a 10-minute intermission, or would people like to continue? Just keep pushing through.
I'm down.
I second that movement.
Third.
Sounds like people want intermission. How about we start back at around 6 o'clock?
Sounds good.
Yeah.
Good.
Okay. Wonderful. See you guys then.
Sweet. Thank you.
Is everybody here and ready to continue with the CDR? Yeah, I see Arshpreet left because he had to head out. We're missing 2 other people trying to. Who's next? Avionics? Okay, so it's Chris. I think we're pretty good to start. Maybe they had to leave because they're busy.
Maybe could anyone who doesn't have their camera on just put a thumbs up if they're back? Okay, awesome. I think that was everyone except Nick.
I'm good. Sorry, I can't find thumbs up.
Awesome. Everyone's here then.
Well, then let's get back into avionics.
All right. Hello, I'm Isla, one of the 2 avionics leads for this upcoming season. So this is the avionics bay, which houses all of the components that will be powering the rocket. So our electronics, as well as a whole sensor suite, the telemetry units, and the altimeters, which control the recovery system. So this slide is more about what is here. Later on, we'll go into the battery system and the structural components individually. So we have 2 main sensors here that are not going to be covered anywhere else. The IMU 2649 from Adafruit, which is going to, it's an IMU. So it's going to have our gyroscope, give us yaw, pitch, roll, acceleration, velocity, all that fun stuff. And BME 280, which is going to give us a bunch of weather data. So humidity, pressure, a couple other ones there. But those are going to be nice. They're going to give us some idea of the conditions that we fly through, hopefully help make future predictions a little more accurate, as well as give us some interesting data. Then we also have the telemetry unit, which is the Big Red B 2-meter transmitter. And that is going to connect to an external antenna to transmit via the APRS protocol information back down to the ground, specifically GPS, and anything else we choose to encode in the packet. We have our 2 altimeters, one Stratologger CF and one Raven 4. We have a camera, which will be covered later in more detail, as well as batteries housed at the center. And I believe that's all of them. And we also have some components here which power the air brake system. So specifically, the boost converter holder, which you see there, and the stepper driver. Since we do onboard calculations for the air brakes, we take the encoder data, we use the information that we have to calculate the ideal position for the air brakes to be at, and we send back that position data via the stepper driver. Future work, this obviously all needs to be manufactured. The flight computer is going to be programmed over the month of July once we have all of the data, everything else has been a little bit more stabilized. And hardware testing, again, most of this is going to be tested as we program it. Next slide, please. All right, this is on to Chris. If you were specifically sharing that one screen, you may have to unshare and reshare so we can see the diagram.
So the rock trees.
I like how you can't uncheck access personal data.
Could someone else share their screen?
Yeah, Chris, can you share your screen and show?
I'm also biased because I put a little ninja edit into it, so I want that to show up.
No, it will be really helpful once we can zoom in because we can see how all of the components across the rocket work, which is going to be really helpful.
Yeah, if you want to zoom in there a little bit just so people can read. Perfect. Yeah, so the main two functions of the flight computer are the direction and step pins there, and then it also provides the logic voltage to like MS1, MS2, and MS3. And then the sleep, Devin let me know, it allows it to go in low power mode, so then we don't have to have the stepper motor constantly having holding torque, which uses a lot of power until we're ready to fly. And yeah, those phases go to the motor, and it's has its own external power supply.
Yeah, I just put it in the chat, but your batteries down there, the 18650s, they look a little backwards in terms of polarity if they're supposed to be connected end to end like that. Yeah, like plus to minus.
Cool. Flipping the middle one 180 degrees would fix everything. One thing I'd like to point out while we're on this, it'll come up later as well in the telemetry slides, but it's helpful to note here, is since we have an external antenna, we are going to have an area of the rocket skin that we're not going to want people to touch, since we do have to carry the rocket out onto the rails and assemble it, we were trying to figure out how we can turn off the entire telemetry system while it's still on the ground. So the fact that it connects over USB means that theoretically we should be able to tell it to not supply any power, and there will be external power going to the transmitter. Most likely, well, yes, there will be, in order to power the antenna up to the full 5Y output. So we're just trying to figure out how we can put another screw switch, like with the 2 altimeters, onto that wire so that we can make sure that we don't give anyone radiation burns while they're carrying the rocket, because apparently that's ideal.
I had a quick question. Matthew mentioned that the stepper driver will be on sleep mode until it wakes up. What tells it to wake up? But under what conditions will it wake up?
Yeah. That is a good thing, though. We have to, to put in to let the program know to start.
Yeah, we're not going to have any communication back to the rocket. The rocket is sending us information.
Yeah, that's what I mean. Like, just tell it just a switch so that it turns on or whatever.
But that won't help. The switch is going to have to be done once it's on the rails. And once it's on the rails, it could be sitting for 6 hours. Well, not 6. We've spec'd it for 4 hours. But we could say once the acceleration exceeds a certain amount, because that will be coming from one of the gyroscopes going to the Raspberry Pi. But we haven't tested to make sure that we can do that. It's possible, though. But if the Raspberry Pi is in sleep mode, we just need to make sure it can still record sensor data. That has not been accounted for.
Yeah.
Sounds good.
Here, sorry, I have a quick one. I don't know if this pertains to the battery more, but those USB charging boards that you have charging the LiPos, I've had an issue using those. I just started experimenting with them recently, and I think they're the same thing as what I was using. They will switch into charging mode if you're drawing less than 60 milliamps from them, which means that they reset whatever they're connected to. So those altimeters, if they're connected to the USB charging board and they draw less than 60 milliamps, the USB charging board will constantly be resetting them. So if the altimeters have some sort of timer on them, then it's going to totally screw with that. So either you need to double check and make sure that those USB charging boards don't do it, or attach a resistor or something in series to just burn away 60 milliamps to keep them active. And like definitely test that, because I spent days debugging something that used one of these things, and that was the culprit. So I don't want you to go through the same thing. It sucks.
Oh, I actually have to add something. This is my fault. I didn't update the connections diagram, but we'll just be charging the LiPos separately. Initially, or before we knew that before I knew that the altimeters had to be separate, the idea was to have like all of our batteries kind of contained and able to charge off of a single port. However, like similar to previous years, I think the idea is to we'll charge our batteries before and then use our little 3D printed clamp and then connect them via, I think it was a JST-SM or something, or whatever connectors we end up using. We'll just connect them once the Avionics bay is assembled.
Perfect.
Sorry, actually, quick question: are those USB charging ports accessible once the rocket is assembled, or are they enclosed then?
So the like I said, there won't be any there won't be charging boards for the altimeters. But the one used for the Raspberry Pi is connected to the or outdated from the renders. It's actually connected to the internal battery section, and so the charger, the USB is, or sorry, the entire battery housing is all self-contained. And can be charged externally from there, but once it's inserted into the avionics bay, it's no longer accessible.
Okay, thanks.
Okay, is that all for this slide? Are we good to move on? Okay, I'll take that as a yes. I'll pass it back over to Carmen. Okay, so I guess we go into batteries, which is Devin.
Cool. Yeah. So the batteries provide power to our flight computer, which is using one of those USB charging boards. Boosts the, I think it's 4.2 out of the 4.2 volts out of the 18650 to 5 volts for our lovely Raspberry Pi, and then separately in that 3 series, connected to that 3 series BMS for 12 volts to our air brakes is another 3 18650s. That 12 volts is also supplying the telemetry system, and the telemetry system is rated for its high power mode between 9 and 16 volts. That second line is wrong. We don't need 9 to 16 volts of power to each altimeter. We're just using, like I said, or we're using those small, I believe they're 600 milliamp hour LiPo batteries, which are 3.7 volts. So yeah, and there's the we have 3 18650s for the 12 volts. We have 1 18650 for the 5 volts, and then we have like I said, 2 LiPo batteries. But there is no charging via USB. And so the batteries, the 4 LiPo 18650s are contained within the center of the avionics sled in a 3D printed enclosure, and then the 2 LiPos are housed in another separate 3D printed enclosure on the camera panel. And in terms of testing, we need to verify the capacity safety factor by actually being able to measure the current draw of our components, because being able to estimate based on random benchmarks has been kind of difficult, and a lot of like specifically Big Red B has been a really big pain to deal with in terms of details for their components, and so we'll have to ultimately test the current draw of our system to confirm that safety factor, and then the future work is to test that and then 3D print those battery enclosures. What's not listed would be also wiring our BMS and our charging board for those different batteries, I guess. Yeah, next slide.
Okay, so here are a couple of the components that we had on the side on the avionics bay. Just wanted to go into a little bit of how each one works. So first one, we got the camera mount, which is subject to change, maybe. It is.
Yeah, this was another members project, and so it's just too tall. Is the issue.
So what we might have to alter it a little bit, but pretty much what happens is actually, Devin, if you want to explain how the camera is supposed to work exactly.
Oh, sure. Yeah. So this was designed by one of Avionics members, Jordan, and he And so this is it has two compliant legs, as you can see on the bottom there, and then the camera PCB is sandwiched between that faceplate, which rests against the inside of the fuselage. And so, upon insertion of the avionics bay, the compliant legs compress, allowing the lens basically to slide along the inside. We'll ideally protect that with some tape or something. And then once the avionics bay has reached its height within the upper fuselage, the lens will pop into place. And then that will be, or that's not the full extent of the fixturing. However, that tells us that we're in the right place for the camera. And then again, what's not updated in the render is two additional fixture holes that will be above and below the lens for, I believe, is a 632 screw or like button head 632 screws to like suck the face panel to the inside of the fuselage. Yeah, that is the camera mount. Did you want me to do the other things too?
Yeah, that'd be good.
Oh, sure. Okay. Yeah, so the battery holder, like I mentioned, has the four 18650 batteries. The BMS is mounted into the lid of the battery holder, and the charging board is actually also inserted into a slot within the battery holder and accessible from the top as well. And so, and yeah, that slides into the inside of the avionics bay, and you can sort of see it in the render, but there are channels along the outside walls of the battery holder that allow the small nuts on the end of the 440 screws attaching all of our exterior components to slide in, and then all the those channels let the nuts slide in, and then those channels are just wide enough to limit the rotator, I guess fix the rotation of the nuts, and then so every fastener on the outside can be tightened down because it's being held by the internal battery holder. Finally, the LiPo holder, similar to previous years, is just a big clamp that squishes our two LiPos for the altimeters, and that's just attached to the outside of the avionics bay.
Okay, we're good to go.
Okay, great. The avionics sled. So the avionics sled holds all of contains all of the electrical components as well as the batteries. It is a lightweight 120 grams. I guess that's the dry mass with just the laser cut plywood and the aluminum posts. I don't believe that's accounting for fasteners, but either way, it is just under 5.5 inches tall from the bottom of the attachment posts to the top of that top plate. And then the outer diameter is obviously the fuselage inner diameter. In terms of testing, assembly rehearsals will hopefully be performed to tweak wire cutouts and spacing of components. Obviously, we don't want to be like screaming at, well, me for designing it at 3 a.m. when we're assembling everything, wondering why we can't fit wires through different spots. And so rather than trying to do a lot of thinking and get it done, or try and get it right the first time, we're going to make it. The laser cut panels being very easy to cut again and iterate upon. We'll be able to tweak things and make sure we're iterating for usability when wiring on launch day. But yeah, that is this. So next slide. I think this is Isla.
Yeah, I think I'm taking this one. So this is basically just to make sure that everyone's aware of what holes we're going to be putting in the fuselage, because we kind of realized there are a lot of them. So they're going to be the 2 screw switches for the altimeters so that we can turn them on and initialize them on the pad, which is where they need to be. 1 screw switch for telemetry so that we can turn it off and then turn it on once it's on the pad and everyone is no longer needing to be touching it. Once again, apparently giving radiation burns to your teammates is frowned upon. 1 hole for the camera and then 2 holes for pressure equalization. The calculations for pressure equalization have been based on a spreadsheet that has previous research in it. Not sure, that's not my area of expertise. And their size is something that we were told and then I forgot before I wrote it down.
3/16, but yeah, I'm just looking at it. I wrote it down.
Thank you.
Yes, 3/16 inch holes for pressure equilibration, 2 of them. 1 3/8 inch diameter hole for the camera, and yeah.
Yeah, so then the 1 hole here, the 1 hole here that has not been accounted for is the one that's going to allow the telemetry, the wire from the antenna to go back inside the rocket. This one hasn't been included in part because it only goes through part of the fuselage as the antenna is embedded in it. But it's not something that needs to be like drilled all the way through at the very end or something. So yeah. Next slide, please. Flight computer. So we selected a Raspberry Pi Zero, small, low power consumption, and it does everything we need it to. It's going to take in all of the data from onboard sensors and then configure it for storage, probably in a CSV format on the black box, as well as configuring a small APRS packet with all the data we deem to be relevant so that that could be sent back to the ground station. It'll also be calculating the position for air brakes, taking in its encoder data and calculating how the stepper motor needs to move to make sure that they are where we need them to be. That will likely be based on a PID algorithm, so that way we can make sure that things are as precise as they can be. So the Adafruit sensors are going to be collecting temperature, humidity, pressure, velocity, acceleration, yaw, pitch, roll, all that fun stuff. And we've calculated 23 I/O pins are going to be used. Most of these go to the strain gauges. The rest go to some various sensors. As mentioned earlier, the camera will be connected via ribbon cable, and the transmitter unit that we're using connects via USB. Analysis and research, a lot of this is going to be done while we are programming and testing everything. We selected a Raspberry Pi, which is a little bit unconventional for UVic rocketry, because this year we wanted to have an easy basis on which to integrate new team members, make sure that everyone felt very comfortable with what we were doing, so that everyone could learn and we could build off of that. So we've decided everything's going to be written in Python, and if we have any issues with speed, we can transition over to C very efficiently, but Python mostly because that's also what Propulsion is writing a lot of their software in, and it's something that is very easy to learn and very useful to know. Plus, all of the things we're using have related Python libraries, which is really nice. Yeah, future work testing. So all the systems will be tested during programming. We'll be making sure we can get information from the sensors, provide information to everything that we need to. Yeah. Telemetry system. Oh, sorry. Yep, I was done there. Telemetry system. So we have selected the Big Red B 2-meter GPS VHF transmitter, as well as the recommended antenna, also made by Big Red B. These will work together to transmit our GPS location to the ground station, along with some data points. So these transmit a signal over a protocol called APRS, Automated Packet Returning System or Reporting System, I always forget. And we can configure a small message, a small piece of text to send along with each transmission, and that is basically going to be encoded data from our sensors. So we can just put some numbers, we know what numbers to expect where, and then the ground station can receive that, decode it, and we'll have all the information that we need to know what's going on. The antenna is 38 inches, about a half wavelength, mounted externally between the carbon fiber and fiberglass layers of the fuselage. So it'll be outside of the carbon fiber, so it is not in an RF non-transparent tube, and underneath the fiberglass in order to protect it. VHF has longer wavelength than UHF, so it was much better for long distances. The setup we're using here specifically is designed for high altitude weather balloons. So in past years, we've had some issues with getting back data and being able to actually pick up all of the packets. Hopefully this means that we will get everything, even with whatever antenna we're using on the ground station side. The tests that are going to be conducted will be the long range distance test. So we're going to have a bunch of people go up and climb Mount Doug and then find another suitable place to transmit from. Great in-reach event. And yeah, so the antenna has to be embedded in the fuselage. So that's up to Aerostructure to make sure that there are going to be no issues there during the lamination process. And that's it for this side of the telemetry system. Now we go on to the ground station. So as mentioned before, the ground station is going to be receiving packets from the rocket in flight. It uses Ubuntu and it's built on the RTL SDR, which is a software-defined radio, SDR. So it can receive packets, decode them, and then provide us with the data. It's built in a Pelican case, so it's nice and sturdy. It's sitting right here. It's got its own power system. Everything's wonderful. Designed in previous years, we've been using it for a while. Nothing needs to be changed yet. We may need to consider checking the batteries at some point, but for right now, everything looks pretty good. And it'll be tested with the onboard telemetry system during the long range test. Next slide, please. Altimeters and recovery system. So as mentioned before, we were originally, we are planning to have one Raven 4 and one Stratologger. However, the Stratologgers are very hard to get right now, especially with all the shortages going on. And they're hard to get even without the shortages going on. So we would like to have one, as they are 1/5 the price of the Raven 4s. But if we are not able to get them, then it will be 2 Raven 4 altimeters. These are going to have external screw switches. So as mentioned before, once we have everything set up on the rails, we can initialize the altimeters. They'll provide a beeping sound to let us know that they are on, functioning, and what altitude they're calibrated for, which we're obviously going to calibrate beforehand. And then these are completely independent, so they have their own power, as mentioned earlier, and then they will connect to the screw terminal you see on the top of the avionics bay to ignite the black powder charges in the recovery bulkhead. They are located in the avionics bay. And yeah, they're both designed for high power rocketry deployment systems, and UVic Rocketry has used both of them in the past, so we understand their reliability and their use. They'll be tested along with recovery during a full integration test to ensure that they can fire at pressure in a vacuum, ignite the black powder charges, and nothing goes wrong. We don't anticipate any issues with this test, as it's been done for many a rocket before. Next slide, please.
All right, so here we got how all the other subsystems will integrate into the flight computer. So pretty much this just kind of gives a little breakdown of how many pins each subsystem's using and each project's using. MaGP-I and Microfluidics are completely isolated with their own power supplies and flight computers and everything. So as you can see here, we got certain communication protocols. The air brakes communication protocol is not right. I have to ask Matthew about that.
I'm not sure what you mean by communication protocol.
So it's just how it's coming through the wire, how we're getting the data. That's pretty much it.
Okay.
Yeah.
Okay.
So I'll need to update that.
Sounds good.
Yeah. So
we'll be getting it directly from the encoders.
Oh, from the encoders, right.
Yeah.
Sorry.
Yeah. So whatever protocol the encoder is using is the one we're going to be using there.
Thank you there. I'm not well versed on my protocols.
Okay. All right. So pretty much the purpose of the flight computer in each one of these for the strain gauges is just to store the data and send it down to the ground station so we can put it on recovery's GUI. for air brakes, it's checking the position and setting the position. So pretty simple. And then black box, we just send all the data there just in case our rocket explodes and we actually want data to come back. So that is pretty much a breakdown of how the flight computer will interact with everything. So do we have any questions about that? Okay, if not, we can move on to the next slide. Alright, here's the full rocketry rocket diagram. I did not get to use SolidWorks Electrical yet. I'm planning on doing that, but I kind of tried to combine a 2D and 3D to kind of give a general idea. So I'll give a little run through of what's going to happen here. So on the really out of focus picture of the rocket up there, you can see the avionics bay, and there is supposed to be an avionics screw terminal right below there, but I rendered this before that was added. All of the components in the avionics bay will route to that, and then from there we will route each and every wire from that screw terminal to everything below. So that includes black box and air brakes. So as you can see in the 2D diagram, the 2 wires will be going to the black box. Each of these will be going through recovery bulkhead strain gauge bulkhead wire holes on the side there, which may need to be changed. I will get back to you once I do some SolidWorks electrical stuff. And then it'll go through the pass-through or the channel on the jam jar, and then go through a connect up to the black box at the top there, and then keep going through the black box channel, and it will then we will have 7 wires to connect to the position, 3 to the position sensor, and 4 to the motor for the air brakes. Harnesses will be attached accordingly once we do rehearsals, but we're assuming that they'll be on the posts of the air brakes and just kind of collected together at certain points. So once I get into SolidWorks Electrical, I'll give an update on this, but that will take a little bit more time to kind of make that if we want that. Yeah, so just a note, there will be as I said earlier, there will be switches on the outside of the rocket. Yeah, and we'll be using zip ties for our harnesses, unless anybody has a better idea. All right, if we have no questions, we can move on to the next slide. Okay, so here we got some timelines. First we got Devin's manufacturing schedule. So Devin gave me a little timeline of what he thought we would, how long it would take to manufacture. So it should only take 2 weeks for the manufacturing process of the whole avionics sled, and then testing will be a part of the, after the manufacturing, along with assembly rehearsals. So those will kind of go side and side to kind of update our design as we go, as Devin said. Next, we got our software. Software timeline. This timeline's a little bit more general, but I gave about a week for each thing. Kind of broke them up into chunks. So I'll just go over kind of what the flight computer is going to do. So it'll store in CSV files, and it'll be quite similar to the hybrid controls project, where we will be handling data and then sending data. So there's a lot of code we could probably take from the old system, from the hybrid system, in order to make this run. So I broke each one up into chunks. Just the first little bits, handling all the information, and then you got some power configuration, GPS storage, and then sending information. That's how I set up the schedule for programming the flight computer. So this should be done by the end of July. Yeah, so that is for timelines. We can move on to the next slide.
All right, so these are our testing outlines. So the recovery integration test we'll be doing with recovery. we'll have a vacuum detonate the black powder charges at the correct altitude, make sure that everything works there. The telemetry system distance test, I gave an outline earlier. We are going to be basically having two groups go up to the top of two different hills and transmitting some packets for a period of time using the telemetry system in as accurate a fuselage replica as we can create to ensure that everything is transmitted and received as expected. Two new tests we'll be conducting are the minimum power endurance test and low power operations tests. So the minimum power endurance test is basically we're going to be operating the entire system until the battery is too low to operate so that we know at what point we need to have launched by. Then the low power operation test, we're going to determine the lowest voltage needed in order to fly. So that way we can figure out at what point we're going to need to recharge the batteries if we're sitting on the pad that long. Everything has been spec'd for a fairly long sit on the pad, but we still want to do these tests just so that we know exactly what the boundaries are. Next slide, please. Next slide, please. Oh yeah, cost and mass budget, which didn't know weren't needed here. So next slide, please. It's also slightly out of date. Questions and feedback.
I have a quick question / like clarification about the pressure equilibrium holes. I was just wondering, like, what was I gonna say? Oh, did you guys like rerun it with like new data and stuff? Because like the Hayek 3 data is going to be pretty different. And
oh, sorry. Did you have anything else to add to that?
Oh, also, like I just had a quick peek, and like they base it on like launch elevation, and we don't know that. So I was just wondering like how sensitive it could be to like the launch elevation.
Fair. Yeah, I modified the cells in that spreadsheet to match what we knew about the 10K rocket right now, and I just assumed Cold Lake as the launch location and altitude, and the 3/16 size for the holes is like a 64th bigger than what the spreadsheet recommended. Yeah, I guess we could rerun it closer to competition if they let us know where we'll be launching. But also I calculated those holes today, so they could use just a second look just to make sure that they're okay.
Yeah, and then you could maybe see like test like I don't think we know it's going to be at Cold Lake, so we could see like how much that affects it. Because if that's not a worry, then yeah, it's just
yeah. Okay.
Is there an issue having oversized holes?
I have no idea. If I remember right, I think Claire was doing the equilibration hole research a long time ago.
I think that was Roger actually.
Oh, okay.
I never looked at that. I feel like the problem might have been like recovery fuselage pressurization, but I'm not 100% sure.
I've got some questions about.
Any last questions?
Yeah. Did you mention anything about the ground station antenna for receiving data from the rocket?
I didn't mention the ground station antenna specifically. The plan at the moment is to keep using the one we've been using in past years, which is currently in storage at UVic. Yeah, it would be great to be able to update it at some point, but since it does work and we've made plans for the rocket to have a stronger transmitting system, there are no plans to upgrade it right now.
Okay, we actually had some issues using it at the last competition.
Mm-hmm.
Even just like issues with, I think, well, definitely getting data links to the rocket, but also tracking it and holding it in position. So I guess once you guys start testing, it'll kind of be apparent if it needs to be upgraded or not. And then also in terms of range of our antennas and transmitters on the rocket, what's the ability of the current hardware? How is there like a limiting range that will 30,000 feet?
They're designed for weather balloons that are going up to about 100,000 feet. So I think we're safe.
So quite over spec. Okay.
Yep.
Perfect.
I had another question about the antenna.
Okay.
What does the connector look like on the inside of the fuselage? Is it like a big connector that's permanently sitting there, or?
It's coax. It connects to the transmitter directly.
Okay,
So
but
the
is the
antenna has a
connector
coax
itself, is it like hanging there in the fuselage? Because it's embedded into the fuselage, right?
Yes. So the connecting wire is about 8 inches long. It'll be hanging into the fuselage. And then when we put the avionics, when we set up the avionics bay, we're going to have to connect it.
Okay, I don't know if it'll be possible to assemble the rocket like that.
Good to know. We can extend the coax cable if needed.
It's the fact that it's hanging there that is the issue. No, it doesn't matter how long it is. I'll have to double check the CAD, but like definitely make a note of that because that's a huge problem potentially.
Okay, good to know.
Okay.
Everything between the avionics bay and the coupler has wiring channels. So in theory, if we tape the coax cable up to the inner side of the fuselage during assembly, we should be able to get everything in there.
Right, but remember that bulkheads, you can't just like materialize a bulkhead past it. Yeah, you have to slide it up the
Is there a reason you can't?
That's the whole reason that strain gauges have embedded wiring with contact pads. Like it's for this exact issue.
Yeah, it's a bit harder with an antenna cable though because it is a coaxial cable.
Right.
That is something we're going to need to look into then.
Okay.
Is it possible that strain gauges omits one strain gauge so there can be a clear wiring channel there? It would make it a lot easier for wiring everything below it, and it would permit. Okay.
Yeah. And then my other question was, so is the antenna 5 watts? Like the actual radio emission is 5 watts?
5 watt output.
Of radio frequency?
Yeah.
Okay. Is that really enough to burn you? That's kind of like a dumb question, I guess, but like 5 watts across
it's
that much.
It shouldn't be, but I don't want to risk it. Generally, any antenna that is transmitting, it is not advised to grab a hold of it, especially not if it's any bigger than like a really tiny one. So it's probably not going to burn anyone. But I'd really rather not find that out the hard way.
Right. Okay.
Unless, of course, you're volunteering to be a test subject.
For sure, if our safety captain was here, they would also not want anyone to be burned.
Yeah, I'm told it's a really great way for the university to get mad at us, and I don't want that.
Okay, I think those are all my questions then.
Okay, so I guess time for flight dynamics to flight to dynamics. So first we have the trajectory analysis. So the requirements set by competition, kind of the same for Spaceport and Launch Canada. 1.5 calibers, stability margin, so center of gravity is 1.5 rocket diameters ahead of the center of pressure, 100 feet per second off the rail velocity, and we are competing in 10,000 foot category, so we want to hit 10,000 feet. That's above ground level, not altitude necessarily. And also we should kind of overshoot because we want to, test the air brakes and stuff. The other consideration is that the trajectory software, like all trajectory software, is idealized. There's no fin, like we can't model the fin feet, the fuselage holes. We can't really accurately model wind, stuff like that. So likely will be lower than whatever RAS Zero is going to spit out. So yes, we used RAS Zero 2 for trajectory analysis, and also kind of just double checked in OpenRocket just to like, sanity check. Although RAS Zero is better since this rocket is going supersonic. So the motor we're using is the Cesaroni M2505 motor. It's about 2,000 something newtons max thrust. This was basically the only suitable motor for that off the rail requirement. There were like 3 options, and then the other 2 were kind of quite oversized. If you guys remember, we had that large thrust motor originally. So we have this is the kind of results as of this morning. I don't know if there's any CAD changes that will really affect it. I guess one note is that's the above sea level altitude. It's kind of difficult to get an accurate apogee without a ground level altitude because like density and stuff changes, all your drag and stuff. Yeah, so we have some nice graphs. Velocity, like I said, like 1.2, 1.1 Mach. And also I assume 6-degree launch rail angle, which is specified by Launch Canada. And 16 G's maximum acceleration. So I think we can go to the next slide, I guess. So inertial separation. So one of the possible failure theories of Hayek 3 was that the nose cone prematurely separated from the rest of the rocket at burnout due to low drag on the nose cone, and then the rocket being much heavier. I stole this straight from Hayek 3 slides, so credits to Nick. So basically, this is previously done by Nick, and I also checked this at the time. And I just redid the calculations with the new drag coefficients and masses. And this is a ginormous safety factor. Basically, it's not a concern for this specific rocket, which makes sense because the loads are a lot lower. And yeah, so basically it's not a failure mode of concern. I tried with various numbers of shear pins and also no boat tail because I know that was a concern in the past. That's kind of it for the inertial separation. So I guess we can go on the next slide. Boat tail. So boat tail, aerodynamic body that reduces base drag on the rocket. It also covers the nozzle. I included this transparent picture so you can kind of see the nozzle sits in that kind of recessed, I don't know what you would call that. So yes, we did a bunch of research on boat tail profiles, and Flight Dynamics member Karnika, she did some research in RAS Aero, and these are kind of the results. Originally, we did have a different rear diameter, but I last minute changed it to adjust the stability margin. That's kind of good to know. We can just easily change the boat tail if we're having some issues. Yeah, in the cases where the boat tail is too long and it extends far past the nozzle, there's worry that it can choke the flow. I found this paper that suggests this equation, where x is the maximum allowable distance between the nozzle and the boat tail exit. But basically, in our case, the boat tail is a lot shorter than Hayek 3, so there's very little space between the boat tail and the nozzle exit. So there's not a lot of concern for that. We're just going to 3D print the boat tail just for sake of we're all tight on manufacturing time and manpower. So I think it just makes sense to have something that's really easy and cheap. So 3D printed out of PLA. Yeah, I think that's it for the boat tail slides. So I guess if anybody has any questions or feedback.
So Avionics is going to need to calculate how much the air brakes need to extend in order for us to hit the 10,000 foot apogee. Might need to talk to you about that later and just make sure that we have a good equation worked out for how much they need to be extended at every point in flight.
There's been previous calculations about it a little bit too, so
awesome.
Just hit me up.
I just realized we hadn't thought about that, but that's why.
Yeah.
Yeah, I can definitely try to help with that if you need more information, though. So just let me know.
Great. So on to Payload. So these are the two projects that Payload is working on for this rocket. For Black Box, this is like the 6th design review that we've done, so I'm not going to spend a lot of time on the basis of the design, more focusing on what's changed, what's new, what analysis we've done since the PDR. And then same with the jam jar. It's been around for a little while, being cannibalized a bit from HIAC 3. So we can go to the next slide. It'll be the design of the black box. So main function of the black box, like has been mentioned in a couple different subsystems, save the flight data, protect it in the case of a fall, and help in the recovery process. There's the module specs, length, mass, etc. All the internal electronics are arranged. Oh, thanks, JJ. It is an acronym, as you saw. Yeah, all the internal electronics are mounted to that 3D printed PLA insert shown in red in figure A. And then that's protected by an aluminum casing made out of 6061 T6 aluminum at the given dimensions. And that's put inside an ABS plastic sleeve, which just adapts the diameter from the aluminum tube to the inside of the rocket. And we talk about that a bit later in rocket integration. And figure B shows the shouldered cross section of the end plates in blue and the tube in red, that this design is more resistant to shear stresses than previous designs, although that hasn't changed since the PDR. And I think that's it for this slide. Yeah, so here's just a pretty basic flow chart for the programming that the Arduino has or will have. It's still a work in progress. Receiving CSV values from the flight computer throughout the flight, and then storing them in the microSD card until no more values are coming, and then activating the recovery system. Yeah, we can go to the next slide. So there's the three aspects of manufacturing are the aluminum components and the printed components and the ABS sleeve itself. Aluminum components have been almost completely manufactured, just like general shape. The tube itself still needs to be shortened by about 1/2 inch because right now it's at HIAC 3 specs, and then add radial holes. I think they're 1032, and those will be drilled at the same time as the ABS sleeve, which also has radial holes. Tools required: lathe, drill press, soldering iron for the internal electronics, counterboard drill for the end plates, tap and die set. Most of that work has already been done off campus. And the future work for that will also be done off campus. PLA insert already printed, shown in figure B. Thanks, Adam. It looks awesome. I have it over there. Yeah, electronics seem to fit. So those will be mounted in the near future. AVS sleeve, like I said, manufactured off campus using many of the same tools as the aluminum. And we can go to the next slide. So black box testing, because the structure and design of this black box is basically identical to the HIAC 3 black box, we're going to be considering the results of the impact test from HIAC 3 black box as relevant. The length of the walls in this one is actually shorter, so that should give it even more resilience to impact. Ideally, we'll be conducting another impact test once we have more of the components ready, just to make sure that our theoretical results are as accurate as possible. And like other subsystems, we'll be doing ongoing testing during development of the software, wiring, making sure everything fits together, etc. And once we have the jam jar, fuselage manufactured, we'll be verifying that everything fits together properly and we've left enough space for wiring passages, which we talk about later in the integration portion. But for now, we're going to be going to the jam jar in more detail.
Yeah, I can present the jam jar. Basically, it's going to be performing a science experiment designed by our science member, Sean Farley. He's been a member of the team for a long time. The experiment is to study whether microgravity will have any effect on gene expression in yeast and possibly also in algae. And we'll be using microfluidics technology to really make that experiment compact. And that's why it can fit in this nice little jar. Total specs, basically it's 0.6 kilograms in mass, not too heavy. It uses, it's going to be manufactured out of a bunch of parts that can be easily done off campus. Like the aluminum parts can be easily done at Scott's dad's home shop, for example, and laser cut plates. It could also be done off campus. Scott knows a guy. They could also be done on campus if we get access to campus facilities. And 3D printing, tons of people have a 3D printer. We've mostly been getting assistance from Adam for our 3D printing. So pretty much the entire jam jar can be manufactured off campus, and the microfluidics parts, Sean is taking care of that in his graduate student lab where he's doing his PhD. Yeah, that's it's all the components fit on a sort of like a metal base plate that then the guts drop into the jar gets sealed up, and then the jar goes into this white PLA sleeve to center it in the fuselage and connect it to the black box below. On the left there, you can see that the middle plate that's highlighted in blue in figure A, it was originally supposed to be made of aluminum, but it was changed to be laser cut acrylic so that Scott could manufacture it with the facilities he has access to. So we did some FEA just to make sure that the switch to acrylic wouldn't be a problem. And no, the safety factor turned out to be like 17. So it's totally fine. Next slide. Yeah, so the controls sequence is that well, a bit of background, the batteries have enough capacity to support the system for about 19 hours. So that's not a problem. Basically, we can charge up the batteries and then leave the Arduino in its on state, just waiting for the trigger where it recognizes that apogee has begun. Basically, there's an accelerometer that will detect microgravity conditions. And upon microgravity, like once it's crossed the microgravity threshold, the Arduino will start spinning one of our control samples. It'll put full power to our spinning motor, which will basically simulate 1G acceleration on one of our yeast samples so that it more or less doesn't experience microgravity while the other one does. And that's just during apogee. So that's only going to be for a few seconds. Then after apogee, The Arduino will turn off the spinning motor and turn on pumps that will pump formaldehyde into the yeast samples to basically kill them and freeze their genetic state in whatever it was immediately after apogee. So that way, when we collect the assembly after recovery, we'll be able to sequence the genes of the yeast and kind of have a snapshot of whatever they were doing after being exposed to microgravity. Yeah, after pumping, like pumping isn't going to take much time at all. So the Arduino will turn on the pumps and then turn off the pumps and go back into its dormant state where it's just sitting there with everything off. Pretty simple control sequence. Next slide. Manufacturing, I talked about it before. The red components you see there are the aluminum parts that have been modified so that Scott can manufacture them with his available equipment, which is a lathe and a drill press. The yellow components are all laser cut. The microfluidics chips, those are the small little biscuit pieces. Those are being done by Sean on campus. And the other two transparent yellow pieces will be laser cut through Scott's facilities. The blue pieces are 3D printed, and everything else is purchased. And the light blue turquoise pieces in the middle have already been printed. Yep, that pretty much covers everything for that slide. Next slide. Yeah, since the jar will be screwed closed, we made sure to test whether it would be safe against the pressure difference between the ground level atmospheric pressure inside the jar and the apogee level atmospheric pressure. And yep, the safety factor is very high. I wrote it down somewhere. I forget what it is. It's like more than 5 on it. Oh, it's down there. Safety factor is 16 against bursting due to pressurization on the way up. And if for whatever reason it depressurizes as it goes up, but doesn't repressurize on the way back down, we made sure to check whether it would get crushed on the way back down. And no, the safety factor is like 53. So the jar is A-OK. Other testing that we'll be doing, the microfluidics pumps have silicon tubes, and formaldehyde, the formaldehyde that they'll be pumping is a very noxious chemical. So we had to make sure that it won't degrade the tubes and leak into the rest of the jam jar. We did that testing a little bit ago, and results are no degradation, no significant degradation. So they are perfectly fine to use. Formaldehyde is compatible with the pump silicon tubes, so that's good. Other testing is just a similar, like as we wire everything together, we'll be testing to make sure the sensors work and the code works as expected. And yeah, also just making sure it mounts to the black box properly. Next slide.
Yeah, I can talk on this one. So
before you do, just one note about the microfluidics thing that I didn't put in the slides. For the electrical system, the batteries are 2 LiPo batteries wired in series to get like 7-something volts. I don't have a BMS wired in there currently. I didn't think I'd need one. Would I need one? Even if I don't plan on having the batteries, like if I plan on having the batteries charged separately, like not in their series configuration, do I still need a BMS for when they're in use? I don't know if
it's fine as long as you're not cycling them. That's when you run into issues.
Okay, cool.
Yeah.
All right, thanks. That's all I had to say about Jamjar.
Okay, awesome. So integration has already been mostly covered previously and in other subsystems. The jam jar mounts with 4 screws onto the top of the black box. The top of the black box has 4 threaded holes. Screws go directly into that. Jam jar has no external connections because the purpose of it is to be a self-sufficient experiment. And we'll be using that Morth we'll be needing the self-sufficiency more in later tests, later flights. The Microfluidics jam jar has 2 passages designed into the 3D printed white sleeve. One vertical, which allows for the air brakes wires to go through, there's 7 of those, and one horizontal along the base to a hole in the middle of the top of the black box, in the center of the top plate. And I probably should have put like a cutaway image of that, but there's a gap in the cavity, or there's a cavity underneath with room for a connector so that the connector doesn't impede the passageway for the air brakes wires. And the black box itself mounts to the fuselage with 12 radial set screws, like it's its own bulkhead. One of the concerns that we had after the PDR was because the black box diameter doesn't quite match the fuselage diameter, there's that extra space between, so then there's the potential for the screws to have a bit more of a bending moment than they would normally. So we did an analysis of that, and the minimum safety factor for the screws is 12.6. So we're content to hold the current design because of that. Like I said earlier, 2 wires come out of the top of the center of the top plate and go up and along the side to the flight computer. And the vertical channel for the air brakes wires is just cut into the sacrificial ABS layer. Next slide. These are our budgets. Again, we thought we needed budgets. So we can go to the next slide. And here's our current timeline for the development of both projects, with the jam jar in red, black box in yellow. All design tasks are, as you can see, are planned on being finished by the design freeze on the 19th. And then included in the period between now and the design freeze, any additional tasks that come up as a result of this review. Once we've passed that, we have a couple of things that we can manufacture right away, and we'll keep manufacturing the microfluidics components that we've been working on and already printed a couple. And then we'll be moving into an assembly and testing era for both projects, with a bunch of time left over at the bottom there to potentially remanufacture parts that didn't survive a second impact test for the black box. And then we'll have to figure out why they failed and do extra design. And you can go to the next slide. Are there any last questions?
Oh, go ahead.
Sorry. I think we might have the same issue with the strain gauge bulkhead and the wires, depending on how they can be routed. Because if we have to slide the strain gauge bulkhead in, then we need to make sure that we can feed the wires coming from the black box to the avionics bay through very narrow channels that have been left for the wires to go through. So I think we might need to revisit the wiring channels in the strain gauge bulkhead. Jay.
Yeah, I was thinking about that a little bit, and if it's wired in the way that I think it's wired, I'm pretty sure it's okay. Might need to make the channels in the strain gauge bulkhead slightly bigger if you're using thicker wire than I expected, but other than that, I think it should be fine. Was that all you had a question about, Isla? Or?
Yeah, no, that was it. I think we're going to need to look at the strain gauge bulkhead though, because the wiring channels are really small.
Once I get into 3D SolidWorks electrical, we can model the wires in there, so that's something we can look into.
Cool. I had another question for you, Scott. Is there a reason that the black box needs 12 radial screws? Because it seemed like it had a pretty high safety factor.
Yeah, we can cut that down depending.
Might be worth matching it up to whatever the other bulkheads have, like 8, just because then you don't have to use like different offsets on your indexing head. But mainly for the fuselage, like obviously if you're 3D printing or whatever, it's no issue to have more. Yeah. But for the drilling the holes in the fuselage, drilling 12 is kind of a pain in the ass.
As long as we like remember to get the fuselage tear out side of things as well.
Right.
Yeah, which is kind of dependent on getting into the school.
But
unfortunately.
Just thought I'd throw it out there. Like if you
But yeah, based on like Aaron was saying, way long ago, like for 6 layers, you know, we're pretty good, and we're probably gonna have 9 layers. So I think it'll most likely be greater than 1100 newtons a set screw. Safety factor.
Yeah, so whatever the manufacturing setup is for the fuselage, we'll just match that and then run the numbers again, make sure that we're still good for that bending moment.
Scott, I had a quick question about, I think it was the black box or the jam container not centering or not being the same ID of the rocket.
Yep.
I think that might lead to some assembly issues, just being a little difficult to locate the centering screws. So if you guys can't increase that OD of the aluminum cylinder, I would recommend maybe some sort of either a 3D printed outer ring that kind of sets into place, or even a lathe piece of Delaware or something that'll locate that assembly in the fuselage.
Okay.
Yeah, it has that.
Well, it has the ABS sleeve, but that doesn't really help with aligning for the set screws. So yeah, we will look into that.
Yeah, I might have missed that in those pictures, but yeah, just something that would actually like actually or radially located in the fuselage would be quite ideal. It's not floating.
Yeah, because right now the way the ABS sleeve is designed, it could just rotate around the aluminum cylinder. So
I mean, the set screws go through the ABS sleeve and are screwed into the black box. So once you locate the sleeve on the black box and then put the set screws in, then the sleeve won't be able to rotate relative to the black box. And then you can slide the assembly in, and the sleeve will make the entire thing's OD the same diameter as the fuselage ID. So it will be snug in there, and then you can retract the set screws and everything should be located properly.
Okay, that wasn't clear in the pictures then. Thanks for that clarification.
Yeah, I think we will need a way, though, of making sure that the ABS sleeve doesn't revolve around the aluminum cylinder until you put the set screws in.
Yeah, that's fair.
Yeah.
Well, circling back to the radial set screws thing, the only bulkhead with a non-multiple of 6 number of set screws is the recovery bulkhead. So check your privilege, JJ.
we need all 8 of those, man.
No, that's the thing. Like everyone else or every other bulkhead has either 6 or 12. So if there's anyone who needs to hop on the multiple of 6 radial screw bandwagon, it's you.
All right. Wait, would I don't know if we can do 12.
No. It's not it's a non-issue because you'll just be last. But the consistency is
Gotcha.
I think is okay.
Okay.
Ugh.
I guess thanks for coming, everybody. That wraps up the CDR. Does anyone have any last comments about the CDR in general?
That also goes out to the YouTube stream. We'll answer any YouTube comments if you have any.
I actually had another question that came up during some other presentations about the avionics assembly, in particular the antenna mounting to the fuselage and routing through the fuselage. That T, I don't know what you call that, but the T module in the middle of the antenna length, that looks quite chunky for mounting either in the fuselage or in the inside of it, and not interfering with either like drag or any exterior features, and also like the integration or like the assembly of all the other bulkheads in the fuselage. If that makes sense.
That is something we're trying to figure out. Big Red B does not provide any size information, so we have no clue how big that T is. Devin took a best guess when he was making it in CAD, and all credit to him. Their picture does not even show the entire length of the antenna, so we can't do like a relative size type thing, which is really annoying. Very much open to changing the antenna. That is just the one they recommend. And so I didn't spec anything different, but hearing all of the issues that it's causing here, I think another antenna will be spec'd. We do need to figure out how it's going to interact with the transmitter though, because if we can't have a cable going from the outside to the inside of the rocket without interfering with everything, we're going to have some serious problems with having an external antenna.
Yeah, I mean, even I don't know. Is there a picture on the slideshow here of that T block?
It's in the telemetry slides. If you go down a little bit more, Carmen.
Yeah, so that top right picture there. So even if you could manage to, are those coaxial cables coming out on the left and right hand side of that?
Yes, they are. No, not left and right side. The bottom center of the T is a coaxial cable. The left and right are the antenna. So they're going to be about the coaxial cable, but without the insulation.
Okay, so, and they look like they're soldered on there. So even looking at it, maybe that T assembly, if we call that for now, is mounted on the avionics bay, and then the two lengths of the antenna are then have like a similar soldering point that like the strain gauges have, and then again slips into place or assembled through afterwards. But maybe you could look at even just modifying that assembly to work. So I think that's
Possibly,
a pretty cheap part, isn't it?
very hesitant. Yeah, I'm very hesitant to modify any antenna that we buy. One, because my radio license does not allow me to build radios, and I don't know if modifying antennas counts in that. But two, they're very specific lengths, and the way that they're built has a very large impact on how they operate, and I don't understand it well enough to feel comfortable taking it apart and putting it back together. If I had one in my hand and I could play with it, maybe.
How expensive is the antenna?
$35 US plus shipping and yeah.
I would almost say we get two, mess around with one, see if that works, sort of thing. But that's more expensive.
Yeah, but if it's
option.
not going to work, then we may as well get another antenna. There are cheaper ones, and it is possible to build your own antenna. Again, after 3 months of research, I just don't feel like I understand it well enough.
Can I just chime in there? Eric, what's his face? Previous Avionics lead Eric, he actually built a custom antenna, and it worked really, really well. Because he worked at CFAR at one point, and one of his
That's the one that we currently use for the ground station, right?
No, like his own antenna, not like a dipole antenna, but like actually a transmitter. And it worked really well. So it might be something to look into. It seemed like it wasn't too hard for him to do, and he just like hooked it up into a network analyzer and looked at kind of how it performed, and it turned out to be really good.
Do you know what platform he built that on top of? Because he didn't have his radio license, so he wouldn't have built a radio capable of transmitting from 10,000 feet.
It was a CFAR job.
So.
But
we'll look at antennas. Very, very likely to change hearing all of the feedback from it. This was the best place to start because it's their recommended antenna. Anyone who has any experience, feedback, knows anyone, please reach out to me. Because again, 4 months of research and I barely know what I'm doing. I've got a giant antenna theory textbook on my shelf, and there's a lot that goes into it. The impedance of the materials that you have, the shape, the size, exactly how everything is placed. So if we have an antenna, I suspect it will be a purchased one rather than a built one, especially since you don't want something breaking at 10,000 feet.
Yeah, just an option that we could do a custom route if we couldn't get something fit within the fuselage. geometry. Did seem hard for him. That's all.
Any more last comments, questions for any subsystem?
There's a question in the, or not question, but something in the YouTube. Give me a second. APRS is a 44 megahertz. Use the link in the budget equation and figure out the FSPL at 10,000 K. You won't need a big antenna. Just 44 megahertz should be long enough wavelength.
We're using 144 megahertz, I believe, is the APRS protocol. Operates on 144, not 44.
Sorry, that's I meant
and okay, yeah. We're working on the 2 meter band. So yes, you could use a quarter wavelength antenna, which would only be 50 centimeters long. This one here is about a meter. So it is half wavelength. My guess is that it is 2 quarter wavelength antennas. Once again, it seems like the antenna is going to change. Very good getting all this feedback because, yeah, I don't understand them very well. But thank you to whoever put that comment.
Okay. Any more last final comments or questions for anybody? Okay. Don't see any reactions, so I think we're gonna wrap up the CDR here. Thank you for coming. I personally think the CDR was pretty successful. Kind of disappointed that Dr. Sulin did not attend, but we will be sending hopefully the video to him if Chris has saved it.
Yeah, it's all set up once it's done here.
Okay, sounds good. So maybe we'll try to send that to him and see if he can help us out with the timeline and manufacturing and equipment and all that stuff. Some just last final admin notes. I highly recommend all subsystems have a follow-up meeting before the design freeze date, just to like have some discussion on any points brought up or some issues or changes that need to be done. Maybe welcome all members in case they have any valuable feedback and just have an open discussion. Budgets, I see a lot of you have them in the slides, which is really nice. If you could also have them completed maybe by the end of this week, that would be good. And then maybe we could start purchasing, because I think like someone said, if we order at once, we could maybe save some money on like cutting some stock or like shipping, all that stuff, which would be good. And yeah, does anyone else have anything to add on? No, Nick, do you want to wrap up the presentation?
Yeah, I don't have too much more to say. Good job, everyone. That's really good. And seems like everyone's pretty much at a finished state. So yeah, keep in mind, design reviews is going to be in 2 weeks. If that concerns anybody here after their kind of in-depth or personal reviews after the CDR, then let us know in the admin meeting this week. But yeah, otherwise, great job, everyone. Looks great. Thanks for everyone who came out. Talk to you guys later.
Bye, everybody.
Bye, everyone.
Bye.
See you guys. Bye.